variables we declared are actually not used, not initialized, and then we later use them. So, and then partially initialized structures using fields before initialization and constructor initialization issues and stuff. So all these things are things that Corelity can help you catch. So if you want to run, if you want to just run a simple, so when I started, they've dropped support for NetBSD as far as I'm concerned. But then if you are using NetBSD and you want to run it, I was actually playing with other OS. I even tried Windows at a point, and because I was struggling to get to working on NetBSD at a point. I was running the scanning. It was just bringing back errors, and so I just realized that okay, FreeBSD has support for it. So I just put NetBSD's code, like ran and pulled it from GitHub, and then put it on FreeBSD, and I ran the scan on FreeBSD, and it actually worked. So, so if you want to use or you want to scan with any of the BSD codes, I think you should try FreeBSD as your host machine. Yep. And then you also need. You can use the Corelity Connect server directly, or you can just fetch your tarball and maybe send it upstream to them. And I think in about maybe 10 minutes or 20 minutes, you get results back through your email or wherever you submitted it to. And then you'd also need your build system for your OS. So after you fetched your code, you have to set up like stuff, like as if you're about to compile the whole code again. So you need a clean build directory, very clean. So with NetBSD, you can do just make clean directory, and then you run. So when you clean your directory, you'd have to, when you go to the website, I wanted to have a small image, but like when I was doing it, I think they are currently down, said they are running some updates. So, but you'd have to download, when you go the platform that you're using, the type there, you see the build for every type or every machine that you are going to use to scan your code, and then you download it on the website, and then you unzip it in your build directory, so like the root directory of your build of your code, and then you run your curve build. It's going to create a curve build directory for you, and then you run, and then you analyze, and then you send your defect to upload results. So this is very simple command to run a correct scan. So like curve build, and then your build directory. No, okay, so curve build, yeah, exactly, and then your directory to be like curve int. So you see a curve int directory in the code that you are scanning. So let's say if you have your SRC code, like your FreeBSD or NetBSD or OpenBSD, you are going to see a curve int directory, and then you see your curve build tool there, and then you see your curve int, and that curve int directory will contain almost everything, all the binaries that you need to actually work with your code to run a full scan on it. And then you add your build command. So with NetBSD, we use build.sh. And so every single build command that you need, you just fill it up there, and then you make sure if you want to, let's say, scan everything in the code, you make sure you get your kernel to include every single module, every single thing that you need, and not leave some. That's if you want everything. But what you want, you can also, things maybe you don't want to scan, you can just comment them out from your kernel configuration, and then this will just, so when you run this command, this will just capture the compiler calls and generate intermediate analysis data for you. So when you're uploading your results, you can either use this curve commit defects, and then when you're done scanning, it's going to put everything to your curve int directory, right? And then you use your stream, the URL to the Corelity server URL. When you set up an account on their site, they are going to show you everything, and then you have a link that you can actually send it there, and then with a node token that you have. So you can either, or if not this way, you can just get your when you're done scanning, it's going to create a tarball for you, and then you can just submit it to them directly. So they will reach out to you that, hey, you're scanning it, so maybe like 30 minutes or 20 minutes time, you should get results on back with your code, and then some patches from them. Okay, not say patches, but pinpoints, some pointers in them to show you where you are missing. So this like is a very simple command that I use if I'm running an BSD source with. So you are to make sure that you've not built it before, because we have a small flag in NetBSD that skips and builds that binaries that have already been built. So, but you wouldn't want that. You want everything like a fresh build. So you should easily just ignore it. But however you do it in your other OSs. So use your core build in the directory that contains your source code file, your source code. And then your covent directory, as I said, and then with this build.sh-u, so let's say to use all my 4 cores, and then my build directory, so where your build directories are, and then your custom kernel configuration. And then when you do this with NetBSD, maybe you can wait for about 16 hours or 16 or 15 hours, I think. Yep, so you can just leave it down and go get some food to eat, have meet family and stuff, and then when you're done, you should have your scan. I think the first time I did it, I did it in the evening, and then it was done like the next morning, I think. And then the next time I did it, I started around 12 p.m. in the afternoon, I was done like 8 p.m. in the evening. So with that one, but I think the next one I left some things out. And you can actually just scan only the kernel. So with this code is actually building only the kernel. So when you do this, you are scanning only the kernel. You are not going to scan the user space code. But if you if in NetBSD, if you don't scan the whole user space, you set up the same command like you are building a user space, like the whole user space code here, so that it runs through all the code that you compile. Because it will need where the compiler goes to, it follows the compiler. So what you tell the compiler to do, that's where it's going to follow you to. And then if you are viewing your results, you use the Coverity Connect Web UI. As I said, I wanted to give a short display, but sadly, when I checked that, when I was spraying the talk, and I think they said they are making some updates. So, but that one's very simple. You can just go to that site and see it. And then you can filter a defect by severity types and file, and then assign and track fixes. So I think there's a pending project in NetBSD that we want our CI to be integrated with this. That anytime someone commits a fix or anything, any code, it runs through it, and then maybe it gives a short output of like what it thinks. But it's not perfect, so it would obviously need human intervention. Like human has to scan it and agree, this is actually not going to help us, or this will have this defect, or this is going to break something, or anything. And then so this is one of the pending projects that we are looking to do, and I've actually not gotten time to do it, but maybe I'll work on it, maybe. So you integrate your core build into and then you run on every command or nightly built it in. I think there are some projects that are doing this. I looked at on some open source projects that have actually started this. I think I've forgotten, but I'll go. So the truth about correct, so currently, NetBSD, when I did the recent scan, we have over 19,000 defects. And I think initially I was like, wow, that's too much. But then as you start going to, you realize that some have false positives, and that's very normal. Maybe sometimes it could be like 50% of what you are scanning. So maybe if you go to 10 defects, you might find 5 useful ones and 5 false positives. But then, as I said, you also need to check. So most of the time I just ping people on NetBSD, hey, check this code for me, or check this for me, and then some say, okay, it's fine, or it's not fine, and then we move on, or we move on yet. So it could have, as I said, false positives could be a lot, but can also be very useful in helping to fix some important bugs. And now we hear of AI, how AI is, today, this AI has found this vulnerabilities in this OS, this AI has found this. And so it's making it like the way AI is moving, we are all aware of how AI is moving. So initially when I was even preparing this talk, I'll be like, okay, maybe people might be using AI to actually scan their code, but if not, this is going to be a very helpful tool for you to do if you want to make any contributions to maybe the OS of your choice. So I'm just here, so for now we can discuss the few bug fixes that we've done. I couldn't list all of them. So the ones that we can actually see and know that, okay, this is some code practice that we do. I think most of us will agree to it, and then we look at how they've been fixed in BSD. So I think the first one was incomplete variable extraction in NPF that I discovered. So that was actually a false positive in variable extraction. But it wasn't wrong with what it was trying to tell me. So as I said, I wish I could show how it detected it, but I couldn't because they were down when I was spraying this talk. So if you have like rules like this in your file configuration, like sales, engineering, and then maybe the whole office, and then you want a rule that could affect both like sales department and engineering department, and then you decide to put them, okay, in your office rules. What happens is that the all rules that are supposed to act on the office only affect sales and ignores engineering. So it was getting an incomplete count of the while loop that actually extracts every single variable in our firewall configurations. So this could expose one's network to unsolicited entry into like engineering in case there's a block on them. So let's say you want to block traffic on engineering, and then an attacker fires packets, maybe very malicious ones, to that field, to that particular IP. In your mind, you've blocked it, but it's something that could easily allow them because it wasn't actually part of what was this. So this is a very simple one that we can. And so this is another one that I also discovered. Incorrect TX free size in a VoIF, the VoIF driver in NetBSD. So we all use VMs, right? We all use VMs. So NetBSD allocates about like 172 bytes per queue during attach on a VirtIO NIC. But then we were freeing only 8 bytes of them in an attach failure path. And I think it was in other path as well. But maybe we can say it's trivial because like when the driver attaches it, it's obviously when you free, you are just losing that memory for now because you cannot use it again. And so it's not something that was like running all the time that could like cause a DDoS or something. It was just like, so maybe it could be trivial, but, and this is what I found. So you have your pointer, the TXC pointer, which is for your transmit ring, right? And then you are trying to maybe free their memory. I think this is something a lot of people do. But it's not intentional, but it's something we do. You omit the pointer dereference to actually free the full byte of it, and then you end up freeing just 8 bytes of it. So instead of 172, you are just freeing 8 bytes of what you are supposed to free. And so you end up losing some memory from your RAM. And so this is a very simple fix that Coverity catches very well. These things are things that they catch very well. I think we had more of this, like 5 or 6 in about a few scans. We had a lot of these things that we were able to catch. And so we fixed it quickly, and then it was good for us. And then another one too, incomplete pre-ROM read on a GEM Ethernet driver. So we're also allocating 2048 bytes for PCI extension ROM data. And then only 8 bytes of PCI extension ROM header were read. This is similar to the one we saw earlier. So if you have like a fix like this, let's say you define your buffer size to like 2048, and then you allocate 2048 bytes for your buffer. And then to contain the the Ethernet header metadata, right? And then you are trying to read that region. So you realize that if you have a code like this is something that was detected. If you have a code like this, the size of buffer ends up returning the size of the pointer, not the size of the data. So instead of actually reading, you might just, so if your data is more than 8 bytes, you end up partially reading it, and then it's just going to break your network device, and so you'll not be able to. So I think this was in NetBSD 10 and 9. So it has been inside for some time now, and then we had to fix and pull this up to 10 and 9. So this is another, so as I said, the converter is very good with catching like bugs like this, like the size of pointer, size of data mismatches. And this is something very common with a lot of C programmers. Like this is something very, very common. We all do, we all forget sometimes. Yep. And then also null pointer dereference in UDF. UDF is the file system used by like DVDs, Blu-ray disc, and many other optical media, like defined for the entire optical media. So if you have like an optical medium that you are using, and then you have your block device like this, and then the UDF sits on it before your virtual file system that you'd mount. And so this was a very funny code that it was able to detect for us. But if you have UDF get node, and then you're trying to get your root directory that you would want to mount, even though the vnode code was checking to see if the vnode was checked in the get node code to see if it's null or not. But then, if it's null, it could return, the error could return a non-zero error. And so it will not allow the code to continue. But then there were cases that if I think the UMP had a certain flag, it would skip the root directory check and then allow the error to return to 0. And then now we don't know if our root directory is null or not. So this is something, and then if we've also checked, so this is obviously maybe forgetfulness. I think that if your root directory is null, you set your error to be ENT for I've forgotten the right error code for it in a BSD, but and then if you have this, you go on ahead to dereference the root directory. So now you know it's null, you weren't able to return, and then you go ahead to dereference it. And so this is code that's also very common that we find in our operating systems code like easily. So I think we had similar things like this that we detected with Coverity. I think it should be like 5 of them. And I think some were also false positives. So we just discarded them, but they were helpful ones. And as I said, if you get your error equals to UDF gets node, this could be doing wrong if the vnode is null, error returned. But then, for correctness sake, computers are one of the unpredictable things in this world. So correctness matters no matter what's in your code. So we ensure that these things are changed. So we gave a simple patch like this to kernel assets that the root directory is not null before we allow to. And then this will even make sense if you get a cache. If your root directory is null, at least you know what your code is doing wrong, or you know where to look into. And then we've been able to catch i386 multi-boot fall throughs that we detected using Coverity. So when the bootloader is probing the part of the kernel image to see if it's like a valid multi-boot. So let's say when you're trying to boot your machine and then your firmware loads the bootloader, and then your bootloader is trying to load the kernel. And then it's verifying to see if, okay, this is a valid kernel this is a valid multi-boot kernel that NetBSD can boot. The bootloader provides metadata that the kernel stores, reference for future use. And so we had a code like this too as well. So for each of them, so we needed a break in between this, right? Obviously, we need a break between this. So when it is checking for the console flag, obviously it's going to use that same metadata to fill the frame buffer pointer. And so if these things are stored in the kernel, and then maybe there will be a use for it somewhere in between, it could corrupt the region to be used. And so we will be just reading wrong data. But I think this was caught earlier before this code was added. It wasn't really long after it was added. So we were able to catch it fast, and then we made fixes to it. And then a double free iMessage 3 in BSD from OpenBSD. But then I think this fix, when you're trying to, when the header buffer IMSG compose iBuff in our TMOX code was double freed on some failure parts. And so I checked with OpenBSD, and they had already updated their code. I think they found a way to detect it earlier, so they updated their code. And so we're late to update. So I reached out to, I think it was Christos who was in charge of it. I reached out to him, and we updated our code earlier. And so we're free of this vulnerability. Yep. And then use of uninitialized variable. These are things that, so all these are things that Coverity can help you easily catch in your operating system's code or anything that you want to use. So Intel Adaptive Virtual Function Network Driver. So the use of initialized variable in Intel's Adaptive Virtual Function Network Driver on the RX ring. And so when the NIC is preparing like mBuffs in RAM, when the OS is preparing mBuffs in RAM, and then handing their DMA address to the NIC, it was actually, so before that, after that, it will have to notify the NIC that, okay, we have new RX descriptors that you would want to put data to in RAM. And so it was depending on this condition, if post, and then you write to it to notify it. But then this post was written like this. So you have like int posts uninitialized. And then there was a while loop that may or may not update post. So it was actually checking to see certain parameters before it will update post to 1. And then that while loop did not actually exit a word to actually make sure that, okay, the post has been written, even if that condition is not checked, to maybe to 0, because it was either a false or a true in the if condition. Obviously, the binary will be needed. But then post was actually depending on code, on a value that may or may not be updated. And so if it's not updated, we know post could contain millions, it could contain anything, 5, any random value from what was used the previous time that memory was accessed. And so obviously you could even be falsely telling your NIC that we have memory for it in RAM, even if it's not, because it was using a wrong condition to send message back to the NIC. So this post relied on a 0, on a 1, and then we also had interrupt handling in the Ethernet 700 series driver. So interrupt handling hardware events that are not when you're sending a packet, but maybe when there's a link down or a link up, something that you're trying to that interrupt that sends it. So it was also it also had that chance of actually returning an uninitialized variable. So we had a code like this, int RV, and then we had a flag like this, and we had a simple code like this, and then RV could be updated to 1. But this was not something very expensive, because this was very trivial, because there was a high chance that this could be true. The chance of the if condition being true was high. And so, but in certain rare cases where this thing is not true, you are returning, and then also checking if it's 0 or 1 in the return code, in the function that called this function. So you are returning a garbage value or a random value to your driver for your network card to use. And also, it had a higher chance of interrupting like your flow of network. So I think right now in NetBSD, we see a lot of my network card is failing, or my threads deadlock, my machine is hanging, but then we sometimes tracing them is hard. You have no idea where it's coming from. So these are things that we are doing small to reduce it. I'm sure a lot of these things are going to catch. And there are over 19,000. I've not been able to go through all the 19,000, but I'm still going through them one by one when I have the time. And so, and then this one too is what it can also catch. The same with uninitialized variable. When you're creating a process, when you're trying to run the process, and then we had an uninitialized variable in the kernel code that was certain process attributes. So if your process is being maybe given the group and everything, the user, we know process have UIDs and GIDs and all these parameters. And so in our code, we had a code like this. So similar one again, and error, if process flag and bits flag, do something. If error, do something. And so we know that this error was supposed to be changed in the if block. But then what is the 100% probability that bits flag is going to be true, or is going to be present in your process flag that you are using? And so we had to initialize error to 0 and to avoid any future error that we might face. So lock release on null or error return. This is something also very common in BSD code that I realized. Like I see this a lot when I'm scanning, so I just add them. So like a simple example is an RPC call like, so when you're activating the transport handle and then you're adding a file descriptor to FDC set, it did not release the lock when it fails. So maybe you're trying to call a function on someone else's machine. We know how RPC works. And then if it fails, your machine could hang, because it could just have other threads that are trying to. So we had a code like this. So you have your socket here, and then this SVC, FD set sock is equals -1, return false. And then the lock has been set on the global lock, but then we return it without releasing the lock. So any thread that wants to hold this lock would have to wait forever, because this lock has it. And so this is something that I also caught to cover it. And then this one too, for loop, limitless for loop. And then you also hold the same lock, global lock, and then you set if your max is equal to null. This is a simple one. And then the out block had just only free of read FDS, but it did not release the lock. So these are things that we do that maybe it could be caused by forgetfulness. People forget when you're trying to write code, but it's also a call that we be extra careful and attentive when you're writing code for our operating systems, because they are the ones doing everything. So so some of the examples of a wrong catch that I discovered that was very interesting to me. I actually did not see it initially, but so in the code that was populating the VLAN Ethernet header field. So this is a VLAN header struct, and then the destination host address and the source host address all have the length of the Ethernet's address length, right? And so this is what the person did. So we have this struct of the Ethernet header. So we realize that the first two fields are, let's see, if this is 6 bytes, we have 12 bytes for first two. So this is what the person actually did. Like meme copy, and then we're taking 16 bytes of it, 12 bytes from the base of the pointer, of the EH pointer, of the Ethernet header pointer. That's going to fetch us the memory address of the destination host and the source host address. And then fetch them singly with one fetch into the header of the VLAN. But then Coverity flagged this as out of bound access because we were trying to read data more than the size of the pointer, because it was seeing the first EH pointer to be 6 and not 12. I actually fell for this, honestly. And then I think I reached out to one guy and he said he's an evil C programmer, and this is what they've been doing in the old times when with evil days. But now when I look at it, I was like, okay, this is not. So these are things that could worry you with Coverity. If you're not careful, you could also guess wrong things, because these are some few things that it gets wrong. Like meme copy like this, I think more of them were very common. False positives like this. Yeah. So, like summary, Coverity helps find OS level bugs early before you can run into any trouble. But then it works by intercepting build process and then integrated CI and review of workflow. This is something that it can really do well and do also. If you want to scan your operating system's code, this is something that you can use. Thank you. Next slide. Yep. Is there any question?
Yes. So you said that you publish the defects with conf commit defects comment.
You said?
You publish the defects with conf commit defects comment.
Yes, you can use
some Coverity Connect server.
So when you go to their website, and then you can register your projects there. So like NetBS has a registered projects there, right? And then so when you go there, and then you can download the build file. That's a core build, and then you can get your oath key and all these things. And then when you go to their man page, they show you how to submit the URLs and everything. Or if not, you can just get your table directly, and then go, whoever is managing the project on Coverity can just go and upload it for scan. And then it's going to send you back whatever you want in the next 30 minutes or something. Yeah.
And what's the URL? What's the website?
You can go to covertyscan.com. I'm sure, yeah, fine. Yeah.
Has anyone asked you questions in your examination of this about using AI to look for bugs?
Nobody has asked me about it, but I'm sure maybe we can give a try to it.
So how do you deal with the problem of volume of these findings, right? Like Coverity findings are typically, you deal with thousands of these sort of bugs in a large code base.
Yeah.
So how do you prioritize which ones are quote unquote important and actually within like an exploitable path? And how do you assign bugs accordingly?
Okay, so when you try to view the defects, you can classify them by defect types, right? So what I do is maybe I make up my mind that maybe when you go, you see uninitialized variables or concurrency bugs, memory bugs, and all these things. So you can classify them, and then you can just maybe decide that maybe this is what you're going to work on. But then.
So that deals with, I guess, what we're talking about as, what the type of the bug is. But I'm actually asking about how do you test if the bugs are exploitable or not? And do you use that in analysis when assigning bugs to engineers or fixing bugs yourself?
Yeah, so if you detect, most of the time when I detect a simple bug, I just look into where it's been affected. And then I get a machine or anything, and then I test it. And then I try to trigger what I think will cause it So if we see the seriousness with it, then quickly I send it to reviewers, like the people who are maintaining such code, and then we patch them as soon as possible. Yep. But sometimes if it's not anything very trivial, I could just speak to one guy and then I say, okay, this is not very trivial, and then I commit to myself that, okay, this fix is like trivial fix. Yep. Thank you. Yeah.
Thank you.
I think on GCC 12,
Okay.
the newer Clang and GCC compilers are adding ways to annotate code to mark up things like malloc, malloc,
Okay. Okay.
and other calls to say, look, check this.
Okay.
So, for instance, this parameter here should match the size of this parameter, things like that.
Okay.
Any thoughts on doing that so that these mistakes get caught earlier during the build process?
Okay, maybe I haven't actually looked at that with the compiler.
You're going to get hit with it when you hit GCC 15.
Okay.
GCC 15 will start complaining at you about that sort of stuff.
Okay, then maybe we'd have to update our compiler. And then, yep.
NetBSD has historically turned on fairly aggressive warning sets.
Yeah.
And so, yeah, if something new comes in the compiler, it's going to end up producing a warning. But that sounds like a very good one at compile time, even though Coverity could catch it. Catching it every compile is better.
Yeah.
Yeah.
You were saying that you started off a build and then you left it overnight for 16 hours.
Yeah.
Are you saying that the Coverty's interception of the build process slows things down a lot? Is that putting an overhead on it?
Yeah, I think it slows it down as compared to like the normal time you use when you're building your code directly. Yeah, it slows it down.
So that would have implications if we were trying to do this on nightly builds, because we're going to need more capacity, because these things are going to take so long to complete.
Yeah, I was doing them on my VM, on the virtual machine. So I think that was also playing a role in why it was taking so much long. But if we, maybe it would be good if you have like a high capacity machine to actually leverage that, because it takes a long time. Like, and I think if you are compiling only the kernel, it's not really that long, because the kernel code is not that much as compared to like a whole complete user space. Yep.
Do you have a sense in your VM of how long a build without Coverity analysis takes?
So I think I had that measure. When I was trying to build, like the first time I built the BSD code like from fresh, it took maybe 6 to 7 hours. Yeah, the first time. But then the first time I did a correct scan, it took me like twice of it. Yep, so it made so much sense.
That kind of matches what I'd expect, which is probably about double time overall.
Yeah.
Have you looked at using LLVM's scan build instead?
Okay.
They also do some extended static analysis, and at least some of the issues that Coverity finds, that will find as well.
Okay.
Onakanaki comment. Yeah, they suck. Project Doma looked at using GCC and LLVM's attempt at mimicking Coverity.
Yep.
And it's just false positive and annoying. So we kind of stuck with Coverity and went down the path of instead marking up code and say, yeah, this is a buffer, here, catch it at the compile time. Yeah. They're getting there. Give it a few more tries.
Any more questions? Okay.
So how does this relate to the previous Coverity stuff that David was doing? Probably that's
This is a continuation of.
Okay.
After I stopped working for Coverity, there was a little bit of dead time there, and then they put somebody new in charge of maintaining it and continued to make the available open source project. So it's an ongoing.
okay.
Sure. Any question?
Did anything that you found correspond to a previously known bug that hadn't been diagnosed yet?
A previously known bug, as in NetBSD.
Did you fix any symptoms that people had already noticed?
No, there were new things that people hadn't seen yet. I think it's a long list. I couldn't write all of them, but hopefully if you come see me, I could share a lot, yeah. But then beware of false positives as well. That's the most annoying part. So the question? Okay. Okay, so thank you very much for coming to talk.
What people do is that when people develop very low-level software, they should use quality of service API, which means that programs that are wrote for FreeBSD is not very portable. Or people might not want to port other software from other operating systems for FreeBSD because they need to use or at least learn the QoS API. And the other reason is that Linux has a lot of available resources. It not only has documentation, but it also has all the Git histories where we can see the rationales for many decisions for hybrid scheduling. What about supporting different architectures and backends? For example, on ARM64, we can use ACPI and device tree to get the information related to hybrid scheduling. I'll talk about this later. In device tree, they have CPU capacity field, which is basically millions of instructions per second. But ACPI also provides something called highest performance in CPPC, which is between 0 and 255. So why is this useful? Many ARM's single board computers have big little core configurations. Also, I think this is what the hardware world is going towards, mix the performance and efficient cores in one single, what we call the package, and then run operating system on it. And FreeBSD is also interested in supporting RISC-V. It might not be the tier 1, but still future RISC-V implementations can have performance and efficient cores and have their own CPU capacity in their device tree source. And finally, I'm working this so the HMP stands for heterogeneous multiprocessing, but this work also benefits the traditional homogeneous multiprocessing. It's because Intel HFI and AMD HFI, which stands for hardware feedback interface, is not specific to heterogeneous multiprocessing. They give feedback like the performance score and efficiency score for each core. So I'll talk about this later, but based on the feedback we get from hardware, for example, let's say core 0 has performance score of 0. Should we place a thread to that core? Of course not, but right now our scheduler only depends on the run and sleep time mechanism. But with this, we have new information that can help making a better scheduler decision. So when we design architecture like this, we should design it very well at the first place. Otherwise, we will change the code. Like, we don't want to change code every 5 months or so. But the principles here is that the HMP, in scheduler's perspective, it's completely observational. What I mean is that the scheduler will not dictate things like, hey, we want more performance on this core. The scheduler will not say this because we already have something called CPU frequency. So we can tune the CPU performance. So why do we have two things that does the same thing, right? And also, in scheduler's perspective, or what I say is that in the scheduler code, the thing is completely machine independent. We don't want to have if-def __ MD64 __ all over at least for ULE, it's 3.5K line of code. We don't want to do that. And it's easy to add new backends. So this is what I'm doing different from the Linux kernel, because on Linux we do a lot of like arch, blah, 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 do something. Here I'm implementing something similar to module declare or declare module and the driver declare. So when there's a new platform or new mechanism of getting feedback from hardware, we can just it's like making a new driver. We just have functions and have structure which contains function pointers to those functions and just register with a single macro. So yeah, it works like device drivers. We can implement this using the device drivers macro. The one and only implementation or the provider interface, which is Intel HFI, which is under review, uses module declare. And you don't need to worry about conflict between multiple backends. Like, let's say there's a system that has ACPI and then Intel's HFI. We can get the capacity information from Intel's hardware performance or ACPI, but each provider will have their own unique priority, which means that the provider with a higher priority will get selected by the HMP subsystem. So yeah, the developers don't need to worry about like, oh, what will happen if other provider is trying to do my work? Like, we don't need to worry about it, or at least the provider developers don't need to worry about it. So it's divided into 3 layers, the core layer, the provider layer, the scheduler layer. This is under work and I'm investigating how to work on this. So today I'm gonna talk about the scheduler layer, but I'm not gonna show you, or I don't have anything to, like, let's say the implementation. The core layer, which is the HMP subsystem, consists of 2 files. One is sys/hmp.header. The other thing is subroutine_hmp.c. It's very thin. I designed this to be as minimal as possible and as much compatible with the most of the feedback interface we have in the role. The provider layer is the device driver. So it's like driver-like interface for registration. It also updates capacity and scores. Updating capacity, I will talk about this later, but it's not accurate term. I would say initialize capacity and scores and also update scores in asynchronous manner for scores. So what's the difference between capacity and score? So capacity is a measure of performance a CPU can reach. Score is a metric of cores capable at the specific moment. It feels like I'm reading a dictionary, but I'll give you an example of what they do. So how are they different and why we need to have tool information for schedulers? Because like if it's hybrid architecture, why can't we just use one unified measure or metrics for making scheduler decisions? Well, the issue is that we have for schedulers, we have very different scenarios and cannot very depend on one thing for a whole time. So capacity is something we borrow from Linux's capacity-aware scheduling. It's expressed, or the initial value that we retrieve from the driver is expressed in MIPS, millions instructions per second. At least that's what the CPU capacity documentation in Linux kernel says. However, they also update the capacity from ACPI. I don't know if ACPI's highest perf is a strict normalization of MIPS or just like a number that the hardware vendor just decided based on their vibe. So at least for the CPU capacity we retrieve from the device tree source, it's calculated by work per hertz times max frequency. In other words, just explain this in easier terms. It's just like when you just boost the CPU to run on max frequency, how much work per hertz does this core runs? But the issue is that, as I said before, the provider interface should be compatible with across different providers. So we need to normalize that raw MIPS value to 0 to 1024 range on boot. Many device trees already have normalized their CPU capacity values to this range. ACPI is 0 to 255, so we need to do like ×4 similar. So the actual capacity stored by HMP CPU is that the capacity of the CPU, and among all the CPUs in the system, we will have the one with the highest capacity. So we divide that and then times 1024, so it is normalized into 0 to 1024 range. Yeah, so we'll see why we do normalization later. And this is mainly used for load balancing, but also used for fitness criteria. The score is only present, so far is only present in Intel and AMD's HFI. They provide the performance and efficiency score. Sometimes schedulers make mistakes. It's not mistakes, it's actually the developer's mistakes because schedulers doing what the developer told them to do. But if one core does too much work, should we place new threads to that core? Obviously not. And if this happens, we can just wait for the developer to fix the bug for the next release, but it's not very practical. So how do I identify that specific core other than the scheduler algorithm? And when I say scheduler algorithm is like, the load of the specific core, things like that. And modern Intel AMD CPUs have something called hardware feedback interface, which is that, for example, for Intel, the CPU will give the performance and efficiency score in table, which is like the score per each core, to the memory region that the driver specified. So if a given core has 0 perf F score, no task should be scheduled on that processor for performance or energy efficiency regions respectively. This is a decision, or at least what the Linux kernel documentation says. But as I said before, we cannot just like copy everything from Linux kernel. Not only because there's like people who say, oh, there are license issues, but also FreeBSD has, I would say, different user base in some cases, and FreeBSD's code is not the same as Linux, although we both say it's general purpose operating system. So scores will have impact on non-heterogeneous platforms like servers. So let's say this is what we see in, let's say, threaded web servers. So one core takes too much work of the web request. And ideally, we should distribute this across different cores. But if that happens, HFI will notify the scheduler that, oh, that core is doing too much work. So scheduler is gonna, based on that feedback, scheduler will replace the thread to like more idle core with, or the core with more higher performance or efficiency score. So yeah, we're actually doing more work than just hybrid architecture support. This also benefits the traditional homogeneous system. The issue here is that I'm not gonna force every user to have this in FreeBSD. The reason is because if you have score, you need some decision code to see, oh, if this core is doing too much work. And it depends on the implementation, but it will have some overhead for making this decision. So I might just, for score at least, I'm gonna make a loader configuration where on boot people say, oh, I don't want to use hybrid or hybrid interface, feedback interface for scheduling. The providers is like drivers, basically, providers. So you might see something similar to this in when you write drivers. Basically, what it says is that the name. So this is for Intel HO. It's a real code that works right now. It's under review in Fabricator. The name of the module, so it will show up on sysdistl, and the mode event, and null. So as I said before, just registering this through the provider interface is not enough. So you need to actually make it a model first, at least for, this is a driver from Intel HFI. And then this will register the provider interface on boot. So yeah, it's similar to the model or driver declaration. So we don't need to spend, or the developers don't need to spend much time, reading the document, actually, experimenting stuff, because I find that this model is more consistent. So those capacitor and score providers are similar to driver declare. This is what the actual implementation. As you see, the registration happens on si_sub_SMP time. So yeah, name, pass the name of the driver or the provider, pass the priority. I will talk about the provider later. And also we're passing the pro function and init function. So both score and capacitor providers use same structures. I could have, merged this in, I didn't need to duplicate this core. I could just write a macro and then declare each struct. But for now, I find this more easier to work with. or at least to debug. And under the hood, as you see in the previous slide, we have name. The probe function, so probably I'll talk about it later, but the probe function is a function pointer for probing. So it's like drivers, right? Like when a driver is probed and then it finds that, oh, there's no device that this driver can work with, then we're not gonna load the driver. Initialization is, initialization init, that's a typo, but initialization happens when the probe returns success, and it will actually fill the capacity or score information. Probe active is just for tracking providers. Developers should not touch this. And to list this, we have entry, so it's like single-headed list. So we can have list of provider candidates, and when we select the provider, it will go through the list to find the best one or the highest priority. So the providers are built in kernel. We're not having that in user space. As I said before, they will be registered on SI sub SMP. So the list will be filled on that time. On SMP +1, the HMP init from the subsystem will be called. The way it works is that if we have a list, let's find the provider with the highest priority. The probe happens. If the probe fails, we search for the next priority. The probe succeeds, we run init. And this happens until there's, we see that, there's no provider we can work on. Like for example, RISC-V, if there's like no device tree information, but also they don't have, or most of RISC-V, I would say, they don't have ACPI. So in that case, for capacity, they will have something called default provider, which is basically just like fill all the capacity to 1024, which is the highest value. So yeah, we do the initializations and we do capacity first and then we do score. The order does not really matter. It's an arbitrary order I chose. The only difference is that score provider doesn't have default provider. It will be, so the pointer to the selected provider for score will be null if we don't find any provider suitable for the system. So the benefit of doing this is that developers don't need to care about like the internal of the whole, I would say this is the HMP subsystem, because I don't want the developers to study or read 5 different source files. Instead, they can just read just man page, or in worst case, read the header file and the implementation file. HMP will do the magic like calculating the total capacity of the system, tracking providers, etc. It is also exposed through sysctl. I will show you the log I got from the Intel HFI developer a few weeks ago. The issue is that, as I said before, the capacity is normalized between 0 to 1024. So if a developer wants to expose the raw value or the raw feedback value from the hardware, they can, they're free to do it, but please use their own sysctl namespace. Don't have it under current points HMP, because someday it might cause namespace collision. And of course, when schedulers want to find a CPU with best capacity or score, HMP will do work for them. So this means that, for example, UL needs to implement its own, SCAD best capacity function, and 4BS needs to implement its own, find best CPU capacity function. So this is the actual working example I got from the Intel HFI developer. Something I need to mention. Okay, so let's talk about active. Is that this provider, the score provider for Intel HFI is active and it's also probed. The default one is probed, but it's not active because the Intel HFI has a higher priority. And then we see which one is the active score and then which one is the active capacity provider, both Intel HFI. And for each core, and here I mean the logical core, so if it's like 8-core, 16-thread system, it will show up 16 CPUs. These 2 flags are now obsolete, but efficiency score, performance score, which is from Intel HFI backend, and the capacity is retrieved from Intel HWP. The reason is that Intel HFI also has capacity provider is because they have some Intel hardware have issues where when the CPU is overclocked through BIOS on ACPI, they will report the highest performance score. So basically, so in future, if we don't address this here, the user will say, oh, why does the efficiency score or the efficiency core is taking all the work? Because in theory, the performance core should take more work. We have capacity 156. In this patch, the author didn't normalize 2024, so you need to times 4 to that. Same for capacity percent. It is capacity in percentage relative to 2024. Here it says 15, but I said before it needs to be times 4, which is 60. So this is basically an efficiency core, which has capacity of 60 compared to the most performant core in the system. Also, one thing I want to note is that the thing that's shown here and the thing that the manufacturer advertise or does marketing is very different because first of all, for this specific CPU, we have P cores, like 4 P cores, and they have hyperthreading. So logic cores 8, so 8 of those performance cores will show up. Also, there are E cores and low performance E cores, and they don't have hyperthreading, so they will only show like 1 core for 1 physical core, because there's no such there's no 2 logical cores for 1 physical core for E and LPE systems. And the last thing I want to mention is that among those performance physical cores, Intel somehow, once the CPU is manufactured, they choose one specific physical core that is more that they deem to have better performance than other performance cores. So you'll see that on some Intel systems, one specific performance core will have, so it's like 1 physical, it means 2 logical, will have higher capacity than other physical cores. And you might say, oh, HMP is not reporting this correctly. But actually it is. It's because the Intel's the API or the hardware interface is not doing what we expect, because on Intel's marketing slides it's like, oh, they're P, E, LPE, so there are 3 different levels. Actually, there are 4 different levels. So this, so far, I finished implementation and the review is on, and I got feedback that this actually works and the reporting mechanism through sys itself actually works. Now the schedule integration. This is the part where I need to read more code, read more, not only from FreeBSD, but also from Linux and probably Apple's Darwin. Thanks to Konstantin, who worked on modularizing the scheduler, we can have multiple schedulers in one kernel binary now, which can be selected on boot time or bootloader. So it would be nice if this subsystem can be independent from schedulers. Like it's not tied to, let's say, it's not tied specifically to ULE, because some people might want to implement their own scheduler in future. So this is why I chose to have minimal layer or minimal core layer for HMP subsystem, because it can be used and it should be used by different schedulers without much difficulty. But for simplicity, let's aim for ULE right now. But integration with FreeBSD or like other future schedulers, let's say eVDF, is definitely possible. Score is the easy part. Capacity is the hard part, and score is the easy part. It's because it's not very tied to any, well, here, ULE scheduler algorithm. It's just simple. So for ULE in scan-pick CPU, what we do is that when we try to find a CPU or core that runs the thread, we first see if the last core that ran that specific thread still has CPU affinity and the affinity is not expired. If that case is false, then we go through a CPU topology and then go to the last level cache. And if the scheduler thinks that, oh, we can run this thread or place the thread to that core, we do global search, and there's like different levels of global search to optimize performance. But when we pick that CPU and we want to integrate the score, we need to tell if that core is good or not, right? Because if, as I said before, if we cannot place a thread that runs place a thread to a core whose performance score is 0. But at the same time, the definition of good is very subjective. So how to find that quote-unquote good score? The best case, the most ideal theoretically, is going through all the cores and find the min. But at the same time, there are like servers who have like double sockets and like 192 cores each. So this is not very practical, because scheduler needs to be fast and decision needs to be made fast. But if you go through all those cores, there will be huge performance degradation. So, but at the same time, like theoretically, all the performance cores can be 0, because imagine you're running like LVM build, and Ninja will distribute the work through all the cores, and all the cores will have low score. So we need to find out which score is the best one, or to be precise, we need to define the border where the score will have impact, and beyond that point, score won't have any impact. So the question here is that should we follow Linux, or at least what the Linux drivers did? On one hand, we should, because people from Intel contributed or wrote their driver and submitted their patch to Linux repo, which means that it's the reference implementation. But on the other hand, sorry for going to the other order, but on the other hand, people or many FreeBSD developers think that the solution for this kind of problem should be specialized to FreeBSD, so which means I'm gonna just copy and paste the code and formulas. So the best approach for this kind of integration is like we did for ULE, test for multiple, like not having set as default mechanism, but test it for like 2 or 3 major releases, and once we are confident that it can be used as a default, make it default in generic. And I'm doing this because like we don't want to have like change to scheduler, because scheduler is it's used by every system. There's no exception, and we don't want to like break any of existing systems just because they upgraded to new FreeBSD version. Capacity is more complex. Unlike score, so for score we only need to, or not only but the most of the part is doing on pick CPU part, which is like choosing the right core for thread placement. But for capacity, the code becomes very different depending on the implementation of the scheduler. Because different schedulers have different data structures to represent as a group of threads. eVDF uses something called a red-black tree to balance, which is like a balance tree where each node represents a process. In FreeBSD, we use several queues, circular queue, and for each circular queue we have run queue, which is implemented using tail queue. But yeah, capacity integration is more complex, and it will vary depending on the scheduler we're working on, which means that the way, the implementation for integrating capacity into ULE will be different from the way we integrate it for FreeBSD. So, let's think about how we can do this. So the easiest method, or the most simple way, is capacity represents the number of threads, and the thread that each CPU has will be proportional to the capacity of that core. This is not a great idea, actually. Why? Because not all threads are equal. They're not doing the same work. So let's say, even if both thread run for 1 second, the work it did under 3 gigahertz and the work it did under 5 gigahertz is definitely different. Like this has like 1.6 times more work than the 3 gigahertz. So what we call is that we need to track accurate task utilization, and it should consider the frequency. I don't think we have this right now in ULE, and that's why I'm trying to defer the capacity integration until we have more improvements to ULE scheduler. And I can say that once we have this in ULE scheduler, we need to call it like something like ULE 4.0 because the implementation will change quite a lot. This is called frequency invariance. This means that not all CPUs have equal. This means that not all threads will run on their same frequency, and we need to do some calculation and normalize it so we can compare to different threads. So capacity can be used for 2 things. First is thread selection. Let's say there was a thread or task that they used full 100% task utilization on their performance core. Should we move that task to, well, like when it needs to be replaced, or placed to a new core? Should it move to like a efficiency core? Obviously not, because the fact that it used the full 100% task utilization on their peak core means that it needs at least that amount of capacity in future as well. And you might ask, oh, but what if a task used 100% task utilization, but over time, it's using less, and then it became like something like interactive task. And like we track the runtime and sleep time, it's gonna decay over time. So you don't need to worry that the fact that a specific task run under 100% task utilization like 30 minutes ago will not affect the decision right now. And we also use it for load balancing. So let's say there are 2 cores. CPU 0 has a capacity of C. Let's just say like 1024. And let's say for CPU 1 it has, for easy math calculation, let's say like half of it, which is 512. And if CPU with half of the capacity runs a task that almost never sleeps and becomes what we call like runs a lot, or taking the 100% task utilization. But on the other hand, the performance core with high capacity, they just sleep very often. So this is not fair, because this is actually a waste of time. Like we can schedule the CPU to have a new task, but making a scheduling decision is already doing another computation, which takes a lot of time and it's not very efficient. So the goal of load balancing is that place that work into the core with higher capacity, and then place that work into a CPU with lower capacity. So there will be less thread migration between cores. So there are a few concerns regarding to like the implementation of these scheduling decisions. The first question obviously is that why we copy from Linux? Not only the licensing issue, but Linux and FreeBSD are not the same, and we should not just copy one-to-one of the Linux feature to FreeBSD. But the issue is that the people who designed things like processors and ACPI already assumes that the operating system has Linux's, not Linux, but they created that concept for that Linux was the first operating system, I would say, to adopt it. So this is something that the hardware vendors intended, and we should not go against it, right? But the thing is that although on the surface this will look similar, but if you see the actual code, I did some exploration on how to integrate it with scheduler, and I can say that there will be no common similar code path that we're gonna borrow from Linux. It's impossible. ULE and eVDS schedulers are very different. Even if we have eVDS scheduler in FreeBSD, in FreeBSD, the run queue is not tied to a specific scheduler. It's actually implemented under sys/run queue.h. So it's shared across multiple, whereas on Linux we had this for a long time ago. And they ask, can we have this in generic kernel or the release build as soon as possible? My answer is no, sadly we can't, because although it would be nice to improve new hardware, we should not break existing. But it does not out of box. But we already have a good, because the ULA schedule, when the ULA schedule, like early 2000s, they had tested like it's major releases, and we can do the same for sure. Personal time constraint, I can't dedicate too much time. So what is the future roadmap? First, the HMP system. HMP system core layer itself does not affect the schedule. And let's also an AMD HFI. And yeah, those two will be beneficial to the existing homogeneous system. So they can be merged earlier than the whole hybrid scheduling thing. And ultimately, because these days laptops have performance and efficient cores, this will help the laptop project that the foundation is supporting. And the third bullet point is the reason I'm deferring the capacity integration, is because there are some upcoming scheduler improvements that Olivier mentioned yesterday, and I don't want to have like create a conflict between his code and my code. Still, I will investigate and test and discover possible integration path while we're making another improvements to ULA scheduler. And since now we can have multiple schedulers through shim layer in one kernel binary, we can see how this works with new schedulers like eVDF. So that's the end of the presentation for today. I'm sorry that I didn't talk much about the actual scheduler decision, or like for example, the eVDF paper has some let's prove using mathematical proof methods so that no task is, every task has its own fair share. I didn't have much time to actually decide or design the scheduler's integration part, but that's a thing that will definitely happen in future. So any questions? Let's go ahead.
With all this new data available to the scheduler, like score and capacity, I can really see a use case for having scheduler profiles almost,
yeah,
optimizing performance or efficiency. Like you brought up the example of how to know which core to switch to when you have the scores available for each core. And you said optimally you would switch to the one with the highest score, right?
Yeah.
But I can see a use case for a situation for performance where you might not want to switch to the one with the highest score, but the one in the same CCD.
Yeah. So preserve the cache data, exactly. Yeah, and we also need to consider affinity, because if we decide that, when we place a new thread, right? If the existing, or the thread that, or the core that run that thread right before, it all, or probably not, because L1 cache is very small, but it might preserve some data related to L1 cache. So this is the scheduler integration path needs to be decided, and I need to actually experiment and benchmark how this works under different situations and find the most optimal. When I say optimal, it works the best on average case, or at least it doesn't break any system.
Profiles and scheduling?
Yeah, they do. They also have something called energy-aware scheduler. So for ARM CPUs, they have table of the energy they over the power consumption they do. The energy they over the power consumption they do. It's a work that we can definitely do in FreeBSD as well, because it's that interface is documented through ARM's manual, but we still need some work on that.
Okay.
Yeah.
I guess conversely for laptops, it would be nice to
Yeah.
especially with so much money being spent on the FreeBSD laptop.
Yeah, exactly. So let's say, for example, on let's say KDE, when we change, so at least I have a Fedora laptop, but I can set the laptop to power efficient mode. So I think the first thing is that it controls the CPU performance frequency. But also, what if it's not? I'm not saying we must do this, but what if we prefer efficiency cores under that system, or like for example, the hibernation we're doing, like efficiency core has better power, it's more power efficient, so we can place threads or tasks to those cores. Yes. Yeah.
So two questions. The first question is, I think, is just simple one about the capacity. It seems like the capacity is like assuming the frequency is static, but it may not be the case. The second question would be, should we just add an extra interface on top to similar to QoS and things like that? Not really just for the scheduling reason, but also you might have some workload you actually do want to place closer to certain CCD. It may not be just because of cache, but also because they're closer to a NIC or something like that, or something NUMA related.
Yeah. So for the first question, capacity assumes that all CPU runs under static frequency. So sorry for not saying this clearly, but in the CPU capacity description, it says they run something called I can't pronounce the name, some Dynochronos benchmark. It basically means that it's maximum frequency. So even though CPU have like base frequency and like maximum frequency, the benchmark will run under maximum frequency. The second question, you should be aware of other, something like NUMA. Of course, that should happen. Yeah, that because FreeBSD definitely runs under systems where there are more than one CPU. So yeah, it is very important to consider that when we actually write code to integrate that score and capacity into scheduler. Yeah. Yes, go ahead.
What kind of information is Intel's thread director providing for us?
So
I've never seen that documented anywhere. Is it just giving us a score of how busy a thread is?
So this is documented in Intel's SDM. And of course, I think no one actually reads the 4,000 pages from top to bottom. So yeah, but at least for AMD, there's AMD HFI implementation on Linux. The funny thing is that they don't describe this in their manual, starting from CPU ID. One reason is because their last version or revision was like 11 months ago, and that was when they merged AMD HFI driver. But at the same time, why aren't they updating their manual? Because I don't think they're gonna make this like undocumented. So I'm just waiting for AMD to document this and release a new manual. I can't contact the developer who wrote the AMD HFI provider on Linux as well. Yeah.
In this talk, you mostly measure performance as a function of frequency, and as I understand, each kind of CPU has its efficiency or performance measure multiplied by frequency. But I remember even from a few years back when AMD Core appears on x86, there was some presentation speaking that some cores are like more efficient, like big cores are better for AVX, for heavy mass, while small cores better doing some background work,
yep.
Not so mass efficient. And it would be, it would not fit into this simplified mass, or if it was decided it doesn't work complications.
So Intel's HFI, and they also have something called Intel Thread Director. The Thread Director has more rows and columns than Intel HFI. They also, as you said, provide feedback like the score for running vector, so AVX instructions or a code with a lot of AVX stuff. The issue is that I think even for Linux, that is only exposed to userland programs. So it's not, the scheduler does not consume, like, let's say specifically AVX, because the scheduler needs to profile that how much of the binary uses AVX. And this works similarly to branch predictor because some of the, like depending on the how the user uses the program might use might go through the AVX centralized code path or just like simple code path. So I think the reason is that if we integrate that profiling mechanism into scheduler, it will have too much overhead. So,
I remember from the presentation I saw that Linux actually it uses hardware profiling of the CPU for different kinds of workloads and gives some cumulative score. Okay, this specific thread over this specific time frame used X amount of fast, slow, whatever instructions.
oh, okay. I'll look into that. Thank you very much.
I just wonder how one would fit with another.
Yeah.
Actually, in HFI, as you described a bit, there are different, you can have performance and capacity and capability scores per instruction mix. So there are different instruction mix, which are called capabilities, I think, or I don't remember the exact term in HFI. And then the thread director also can tell you, okay, this thread is more in this class of instruction mix. So maybe we can actually leverage it, but I'm not really sure. It's just theoretical at that point, but it exists.
Yep. Any other questions here? Okay, if not, I'll end my presentation here. Thank you very much.
Hello, everyone. I'm Eugenio. I'm a third-year student, undergrad student at University of Edinburgh, where I study computer science and mathematics. So it's quite far away from here. And I previously interned at Networking Operating System Laboratory at University of Edinburgh, where I'm working on this specific implementation that I will present. And I worked at Apple, where I work in the Chorus team. So I'm very passionate about kernels, but this really is my first time working on FreeBSD. So I'm very happy to have any discussions and learning more from more expert people. So first of all, what's SMT? So SMT stands for Secure Message Transport, which is a protocol designed for data center RPCs. And it is message-based, and its objective is also avoid header line blocking. So in addition to that, we also have encryption through TLS, which grant us property like confidentiality, integrity, and non-replayability. So first of all, a little bit of background. We all know that the internet is not very safe, so because of that we need security. But are data centers safe? So in 2013, Snowden revealed the NSI captures all the data center traffic. So people realized that encryption is needed in the data center as well. So TLS started being used inside the data centers. For example, Meta has an article about it and how they use encryption. And also, data center is not really trustworthy, also because there are either malicious insiders that might spy on your traffic, or either you might have compromised tenants that might cause problems to other tenants. But we know that TLS is built on top of TCP. But TCP is not really suitable for data centers, or because of its tail latency caused by headline blocking. So we have two cases. First of all, we have packet loss. For example, if you have a queue of messages arriving, we have some packets arriving, and one of the packets in the middle get lost, then the receiver needs to wait for this specific packet before it can process the remaining of the packets. And another case would be caused on the CPU. Well, for example, if a big message arrives and a small message arrives after, the small message is blocked behind the big packet while the CPU tries to process the big packet. If instead we try to avoid this headline blocking problem through having one connection for each message, this still causes problems because all the connection will share one CPU. So some connection will share a CPU core, some other connection will share another CPU core, and this will cause the problem that a busy connection might might cause problem to another connection, might delay it, and so on. So since TCP is not fitted, why we not think about another protocol? So for example, QUIC. Well, QUIC is designed for the internet, where latency is the milliseconds, where in the data center is more in the microseconds. And also, you only avoid the headline blocking problem only in the path case and not in the CPU hotspot case. So the CPU hotspot case is the one where I explained where a large message blocks a smaller message in the queue. And another problem of QUIC is that there's a lot of software overhead to avoid middle bus ossification, because in case we want to change in the future, the quick protocol get changed. So if TCP is not okay and quick is not okay either, we need to find a new protocol. So to build SMT, we can use HOMA as a base. And why HOMA? So since there are no protocols that combines both TLS encryption and message-based abstraction, we can use HOMA as a message-based abstraction to build SMT on top. So it has a lot of features that are needed for data center, for like high throughput, low latency RPCs in the data centers. As you can see, there is like scheduling for shortest remaining processing time. That's very good for like small messages that we send first. And for example, we have offload as well for TCP segmentation that would be very useful for the SMT protocol. So why we don't simply plug TLS on top of HOMA and just let it work and call it a day? And that doesn't work because let's assume we have a single TLS handshake between sender and receiver. And TLS, we know that TLS assumes that the message or the byte stream will arrive in order. But that's not necessarily true for messages. They might arrive in different out of order. And that decryption will fail in that case. So we don't like that. And if you try to do per message handshake, that'd be very, very slow since we need to do a single handshake for every message. So instead, what's the idea of SMT? So first of all, we assume that the application does handshake by itself between sender and receiver. And so application do the handshake with all the application, then the application will send its IV and the key to SMT, and from then on, the application will be allowed to send plain text messages directly to SMT. And SMT will encrypt it and create the RPC necessary to send it to the other SMT that will give it plain text back to the application. So what are the two important key design components of SMT? First of all, the on-wire format is based on the TLS record protocol, so that in this way, TSO offload is possible. And each message has its own TLS record sequence space. So this protects the protocol from replay attacks. So we start from the first goal. Let's see how we reach this goal by how do we do TLS offload with SMT. So what is TLS offload? TLS offload with TLS. We first see that we have a packet with a header, and what happened is that inside the NIC, where TSO and with TLS offload is enabled, is that this packet get chunked in M2 sized packets, each with a copy of the header. And at the same time, inside the NIC, the payload get encrypted. Oh, sorry. So this works. So TSO is specifically built for TCP, but we found that TLS offload with TSO work for non-TCP packet as well. So it doesn't necessarily need to be TCP in the sense that in the IP header, the protocol field doesn't need to be TCP. As this works, as long as the header is similar to TCP, so it's TCP-like. Sorry. So the protocol form, the header format is that, for example, we see that in the IP header, there's no TCP protocol, but its own TCP, its own protocol number. And the transport, we have the source port, the destination port, message ID, and the message length, and the TS offset that we'll explain later. And in application, we have a TLS header, and then a series of message offset, message payload, and so on. Sorry, the presentation is bugging out. Why is? Okay, so the packet payload will be composed by, in the first packet will contain the TLS header, the message offset, and the message payload. And another packet, next packet, for example, will contain only the message offset and the message payload. And in case of the last packet, you can contain the message offset, message payload, and the TLS trailer. So now the entire TLS record, so the entire TLS record from TLS header to the TLS trailer containing every offset and every payload. And we can have inside the TLS segment, we can have multiple TLS records up to 65,000 bytes. So now I'll show how it works, the segmentation or reassembly. And for example, in this case, let's say that we have an application payload, or application message that gets split over two TSO segments, each one with its own TLS record. So when it goes through the NIC, what happens is that it chunks the packet, the two TSL segments in multiple packets. So in this case, the left packets becomes three different packets. Well, here, the TLS header and the message offset and the message payload. Here, only message offset and message payload, and here with the trailer instead. Next, the payload gets encrypted within the NIC as well. And when it arrives at the receiver, the NIC will will reassemble it back through the IP ID, so the IP field inside the IP header, into the TLS segment, TSO segment. The payload is still encrypted, and then the decryption can be done through the TLS record sequence number. So now we are obtaining back all the offsets and the payload. And then SMT can reassemble it back to the application message through the message offset inside the payload. So in the case, we want to do out-of-order message delivery, right? And the problem is there are multiple sequence number spaces. So for example, if a message sent with 1 and another message sent with 1 as well, then that can create like duplicate sequence number. And then from that, we violate in the replay principle. So we can avoid that by combining the message ID, so each RPC has its own message ID, together with the record index. Through that, we guarantee a unique like sequence number, and from that, replay is not possible anymore. So here an example, for example, message 0 can be split into different packets, and each one has each different record, and each record has 0, and the next one has 1, and same for the second case. And the last case, since it can be contain only one TLS record, only has index 0. So TLS offload is essential for to like make it very efficient. But the problem is that the sequence number expected from, usually for example, from a Mellanox NICs is that the sequence number is in order. So we could update the NIC with the expected sequence number. So what will happen always? So NIC, what usually happens at the NIC is that when it receives a packet with a sequence number, then it has an internal counter and increase it. And when next packet arrives, then it knows that that's the expected sequence number and so on. And the problem is that with message-based transport, this is not guaranteed. So what we could do is that we could through software implement, like update the NIC expectation of the sequence number, but that's kind of problematic. For example, it's not really atomic, because let's check this example. Let's say we have so we have S1 and S3 that are real messages, while R1 and R3 are like fake packets to change the NIC expectation of the sequence number. The problem is that if we try to do that, what might happen is that S1, S3, and R3 and R1 might not arrive in the correct order. So for example, S1 and R3 might come together, and then that causes problems. So instead, this is why per message record sequence is very important. Because since we have the message ID, we can now separate the indexes, we separate the messages into different flow contexts, and from that, the encryption doesn't fail anymore. So why SMT on FreeBSD? So FreeBSD is a very good data center operating system, and has a lot of users in networking and storage. And at the same time, SMT is a very good protocol for data centers. It's specifically designed for that. So it could be FreeBSD could be a good place to implement that and have a good use for it. So this is the API currently implemented for SMT. So why is SDP that? The reason is that at the time it had a different name. So I implemented with SDTP instead of SMT. So don't worry, SMT and SDP are the same thing. And the API uses socket. We create a custom IP protocol for that. And then through setting the socket options, we can enable TLS or disable it. So we have either enabling through the receiver path or the sender path. So they're two separate. So one could have only the receiver path having TLS enabled, and the sender path will be using normally HOMA. So this is an example how it would be used. So we could put all the key IV in the cipher of the TLS, and then we can also add the P address and the peer port to set the TLS enabled. So why we need the P address and the peer port is that we specifically set the TLS for only the specific peer. But there's also the option to have peer address 0 and peer port 0. In this case, these parameters would be used for all peers if they don't have a specific TLS for them. So this is an example of what will happen if you set 0 for both of them. So in this case, both peer will be using the same IV cipher and parameters. So send message. So for sending message and receiving message, they're using the normal API that's expected. So in addition to the payload, you can add an argument through the control bus. For example, you can either set ID or the complexion cookie, and if you set ID to 0, it's a new request, while setting to another received RPC ID is a reply to the specific RPC. Similarly, receive message uses the same normal API. Through receive message, you can there's a control buff to get the ID, the RPC ID of the message. So code organization-wise, we have module to deal with like module load, unload, like registrations. HREC is for like all the socket entry points, and PCB is dealing with like PCB, RPC the same, and peers dealing with like the peer table and so on. So input outputs for receiving and input packets, and output deals with the output, and context deal with the TLS context integration, and struct are for like global state and UML pools and metric related stuff. So SMT is implemented as a loadable kernel module, and this is the way to declare a module in FreeBSD. So we have the declaration and the module version for dependencies. And then we have this is the mode event handler that's put inside the mode registration. So we have mode load where all the like struct are initialized and all the IP input registration is done, and proto SW's registration is done there as well. On unload the inverse, and this declaration make the module visible to the kernel, but still doesn't allow SMT to be connected to the socket layer or to the API layer to receive packets. So we need to do more registrations. So here is the application layer that speaks to the socket layer, and then we have here the NIC where all the packets arrives. We'll give it to the net ISR layer, and from that the net ISR layer will give the packet to the IP layer. So we want SMT to sit beside TCP and UDP, and we don't want to make it. We want to make it its own protocol and not something, and not to encapsulate it around UDP, because we don't want to have overhead not necessary. So how do the transmove protocol communicate with the socket layer and the net ISR layer? Through two registrations. So for the socket layer, we use proto SW register, and for the second registration, through IP proto register. So now let's go through each one. So this is the proto proto SW field, the structure where we have all the generic socket like function that are necessary to make a socket work. And we, for example, here SD bind. So what happens is that when a user calls bind, will go through the syscall and then to the socket doesn't know about the existence of SMT, but it knows that by going through the SO proto table, we find our correct implementation of bind. So why we choose diagram instead of any other type of socket interface is because, for example, stream-based interface will not work well with SMT since it's message-based. So we need to have diagram. So SMT preserves message boundaries, but it's not like UDP where the message need to be inside it need to fit inside the MTU size, where in SMT, all messages can be bigger than MTU size. So now we consider the IP proto register part. So without that, all the packets from SMT will just go to the IP input, and when they see that there's the protocol number for SMT, will just reject it and drop it. So the registration is composed by two parts. So we have STTP input, where all the packets arrives. So we have the mbuf containing packets, offset pointer that contains the offset of the buffer from the buffer where the IP and IP protocol headers contain. So, and proto will be our protocol number. Control input instead is for like ICMP related protocols and events. So we're not very interested in that. So after registration, the IP input will redirect our packet to our SMT input, where we actually deal with packet. So the control flow looks like this. So we have a packet validation for like type and for length. So each type of packet, apart from data, has its own length. So we need to validate through that. And then we try to find the PCB for it. If we don't find it, then we reject packet. And then we check if the packet, so if packet is client, means that the packet is the client side of an RPC. In that case, you can either look up or create a new server RPC. Since in the other case, when the packet is server, we need to look up and not create, we cannot never create a client RPC in the case, because in the case the packet is server, it means that the packet is a reply, so we expect that we already have the RPC for that, since we created the RPC when we send the message. So in the case the packet's data, we insert the packet by offset, by message offset, and if it's complete, we mark it ready, and then we hand it off to the receiver. Otherwise, we handle the different packets based on what type they are. So on the receiver side, we check when we call receive message, we call this specific function SO receive, and from that we check if the user asked for a request or a response RPC, and then we check the ready queue for the specific request or response RPC queue. If nothing is ready, in that case, if you have the specific flag that says that's not blocking, in that case we just return E error again. In the other case, we first rip the dead RPCs. So before going to register our interest, so interest is a way to is a structure that indicates that this thread is interested in this specific RPC. And then we pull briefly. If we don't find any RPC, in that case, we go to sleep. When we do find it, when we get the ready RPC, we claim it, so the other thread don't mess with it, and we decrypt the message. So we decrypt the message in the receiver side and on the IP input side, and then we copy the message to the user. So in the center path, we have two options. So if ID is equal to 0, then we create a new client RPC. Otherwise, we need to look up a server RPC. And then from the message, we compute each packet payload size, and from that we build the packet mbuf and IO vectors and fill the SMT headers and the TLS header. And from that, we copy the user data from the IO and encrypt it. That's wrong. And from that, we fill the IP output manually. So the reason why we fill it manually is that we want to change the values of the IP ID, and that's not possible if we let the kernel do it, let IP output do it. So how are packets represented? Each packet is a chain of mbuf. So the mbuf contains field like mnext, a pointer to the next mbuf, then a pointer to mdata, and the mlen will represent how long the mbuf payload is, and then we have mflags, which will indicate the type of the union data, where it can contain multiple different stuff. So this is still a simplification. So during implementation, it's important to be careful to deal with that. So based on mflag, it can be either no flag. In that case, the specific field is just pure data. In the case of flag packet header, we'll have some metadata about the mbuf chain, and under it, next it will be the data, or either can be X. In that case, it contains external memory. So we have the first part will be unused, and then bottom that will contain information about the external memory and the pointer to it. Or it can be external pages, and in that case, contain multiple pages, and that is very useful for TLS. So I use it I need to use it in the sender side to encrypt the data using external pages type of buffer. So when we receive packets from IP output, usually we have either or this format based on the length of the packet. So in case, in the smallest case, would be packet header, and the entire packets will be contained within data. In the second case, if the packet can be contained within data and another normal packet within a packet header mbuf and normal mbuf in the case, or if it's very, very big and can be contained in the first two, we'll have a packet header chained by our external mbuf. So here are all the structures for SMT. So this contains all the global states. We have the next RPC ID. So that keeps every RPC ID unique. Then we have grant of RPCs, short of RPCs. But in my implementation, there's still a prototype. Still doesn't have any grants implementation. Then we have metrics, is control parameters to make it tunable. And the most important stuff is that we have the PCB by info that contains every PCB by destination port, and the peer tab that contains information every peer. And we have the UMA zones to like allocate very quickly memory for RPCs, PCBs, or peers, or other necessary structures. So within the PCB info, we contain all the PCBs. Each PCBs inside have a in PCB that is used for IP protocol. And each of these PCBs have two maps for RPCs, one for client RPCs and one for server RPCs. In the case, so each of these RPCs can either be active or dead. So if it's dead, it means that we can clean all the memory inside it and deallocate it. And client RPCs or server RPCs, so client RPCs can be in the ready request list. So when a user can try to receive a message, you first check in the ready request. And same for servers, that will be in the ready response queues if they're ready. And also we have TLS context map here as well. So we have a map for all the contexts we created through the socket option, set socket option function we saw in the socket API slide. So also all the PCBs contains the request interest and response interest. So we already explained what interests are, but I'll explain again. So interests are for waiting thread that are interested in our RPC. And so in this case, the thread doesn't need to check every RPC to find something they're interested in. And and the PCB doesn't need to check every thread to see if they were interested in, so we can just find it. And each RPC contains information about the parent PCB, the destination port, their ID, their like specific TLC context, the completion cookie, and their own state. So it can be either outgoing, incoming, in service, or dead. And it contains also information about when they receive the MBUF. So we have a list of MBUFs when they receive, so they can keep it. So, for example, if our MBUF, our packet in the middle get lost, then we still can't create a chain or MBUF, and then when it arrives, we'll just plug in the middle. And same for message, and for message out, we still have an MBUF that we want to send, and the bytes remain that we want to send. The total length represents the length of the packet, so the total length of the payload inside the MBUF. So for TLS, our interface is very similar to the KTLS interface inside FreeBSD. So it would be very nice to use it because we want to create sockets, we want to create like negotiate keys and create like sessions. The problem is the KTLS session layer that manages all the KTLS sessions and like queues and K-threads, you expect TCP. So without modifications, that make it very, very hard to use it. So so instead, we use the lower layer that is called by the KTLS session layer as well, that is actually responsible for decrypting all the so like responsible for the actual decryption and encryption. So we can use these internal functions, but the problem is that all the like KTLS session lifetime, and we need to create our own, like manage our own MBUF to be decrypted or encrypted. For example, like we said in the case of external pages MBUF that are needed to be encrypted. Regarding concurrency, SMT doesn't need to acquire the socket level lock-in since every RPC, since we don't expect RPC messages to arrive in order. So we don't need to have socket level information to like keep track of like the data like incoming in order, while TCP sockets, since they need to have data in order, they need to be locked for each packet that arrives. But the problem is that since the current implementation is still a prototype, it still looks like TCP. So in the future, potentially, it can be better. Regarding performance, I did a small benchmark. So this is only for like the ping pong test case, very simple. One client, one server, send a message, send a single RPC to the other, and then it replies. So in this case, we have around 25 microseconds for every case until 2048. And from then increases because from that point on, all the message cannot be contained within one single MTU-sized packet. So they need to be contain multiple packets. So the stuff I still need to implement, we have in transmissions. So for now, I assume that it's lossless, the path. And I need to implement grand scheduling. So right now, we just span packets to each other. I still need to implement IPv6, since now it works only for IPv4. And for now, decryption and encryption is done only through software. So I still need to implement the hardware TLS offload part. Conclusion, that's the presentation. Here's the, for now, the prototype for SMT. And thank you. If there's any questions. Yeah.
I think you sort of answered. So you also you use the in-BCP lookup, right?
Oh, I currently don't use that. I shall probably use it in the future. I want to implement it in the future.
So you do the port lookup yourself?
Yeah, it's probably a bad idea.
If you do the port lookup yourself, why would you use BCPs at all?
I wanted to port it to using MPC lookup in the future. And then I need it for...
So you plan to use it?
Yeah.
I see. Also, when you register the IP protocol, you also register CTL control input, right?
Sorry?
So when you do, it's 20 slides time. Yeah, where you're plugging. Yeah, right here, yes. So the CTL input, it will react to ICMP messages, right?
Yeah.
So that means that the other side should generate ICMP messages. So when you got port, there is nobody listening to the port, you generate ICMP messages, is it right?
Oh, you mean the case where I haven't registered yet? And then, sorry.
Or bad port.
Oh, bad port, okay, yeah. Yeah, because,
You
yeah.
do generate ICMP messages.
Yeah.
Okay.
Which means, by the way, I don't think you can get away with no locking, because either if you're writing to the socket and you've got a message you validated, you've got to append it to the queue of inbox.
No.
You got to lock to protect the queue. That's what the socket left to lock.
Yeah.
The other type of locking is going to be for your PCB, your PCBs, the like INP, WLock, RLock, and that's where you check there's locking for managing the PCB info stuff Lev just mentioned. So finding if you have a valid port or not. You've got to check something to see if
I
the
see.
message
You generate ICMP messages.
So you're going to be stuck with some locking, because if
Yeah.
you're trying to use a response to valid request that I sent, for example, in the data structure,
Yeah.
you've got to deal with, concurrency with that. I think you're probably stuck with almost as much locking as TCP because of those things.
Oh, I
You're
see.
just checking
Yeah.
different things.
I think you can easily use the PCB database.
Look into it, but it's like a first version sometimes. Because INPCB info is scary. You have to cut, but it's not all you want.
I think it's easy to use than to write your own. And one more question. Fooling the NICs to give them a non-TCP header, but still perform TSO. How many NICs have you tested with this trick?
So right now, I know that works on Mellanox ones,
So Mellanox,
and other than that,
Chelsea
I'm not sure.
Chelsea will do the transmit side. I read the paper for Linux, because we talked about it 2 nights ago.
okay, so they also do.
So effectively, there's just more fields in TCP option center, and normally when you do TSO to NIC, you're effectively telling like how big is your layer 3 header. And so if you just make that big enough to tell it the offset of how much of the incoming thing is the header you have to copy each packet, it's not going to care. It's just going to copy the extra bytes as if they were TCP options or something.
Yeah, yeah.
So I think it does fall out because it looks enough like.
But it needs
The C side, I believe,
the offset of the.
The checksums and things, and those are it's just it's parameterizing it, right? It's when you do a TSO, usually with some kind of NIC, it's like my IP, my layer 2 header is this long, it has a checksum, it's at this offset, so it's always 16 bits. My my layer 3 header is this long.
Sequence number.
Oh, that's true. Well, I wonder. I bet they use like the message offset because the paper talks about the fact that they really try to make it look like TCP.
So the message offset needs to fall exactly where TCP sequence falls.
Yeah, I think they've designed the protocol to basically do that on purpose to make this possible.
Thank you.
Okay. Okay. So.
Okay, well, hello everyone. Thanks for coming. Today, welcome to GeoMan, bringing Gparrot-like operations to FreeBSD. So let's first start with the story of a noob FreeBSD user. One day, our character wanted to move his FreeBSD partition using UFS, nothing too fancy, no CFS. So he looked up for Gparrot on FreeBSD just to find nothing. He then looked at a forum and looked at a question from 2012. Is there a graphical partition manager for FreeBSD? And then he went to the fresh ports just to find nothing. There is no Gparrot in FreeBSD. What a pain. But he then he said, I'll become brave. So he did a few things. He first had to read the handbook, like every FreeBSD user, at chapter 21 about file systems. He then discovered about Geom. What Geom is, the popular framework about devices and raw storage. He then discovered he had to use Gparrot. And he took some time to learn Gparrot. Because this user was very insane, he read chapter 8 from the Absolute FreeBSD book. And what happened at the end? Well, he had an almost epic comeback. He now is a almost professional partition manager. So he's going to move his partition 20 gigabytes to the right. But he just found out he can do a backup because he doesn't have enough space. So he couldn't move all his partition, and all this work was for nothing. And he also still misses what CFS is. He doesn't know JLH label, and he is still confused about what is a Geom consumer and provider. So what's the moral of the story? FreeBSD doesn't lack a powerful storage tool. It certainly has, in my opinion, a better ecosystem compared to Linux. Either Geom framework, programmatically via libgeom, you import the library or using commands. And also, obviously, native CFS support. But it lacks a unified interface that brings those tools together. So let's first take a look at how you do today partition management in FreeBSD. So let's say, for example, you want to create a partition. So maybe you first look at the disk you have. After recognizing on which device you are going to add the partition, in this case DA0, you then use type gparrot add, you add UFS partition, you label it with the name data, and obviously you have to create the file system on it. So it will be under def GPT data because you're using a GPT label. And then you have to mount it. You make a temporary directory where you create a directory under mount, and you mount it, your new partition. You also may want to grow a partition. You look again at the partitions at your disk, DA0. Maybe you want to resize it. So in this case, a random partition at index 2, it will grow at the most space it can. But as also, if you grow the underlying partition, you need to grow the file system too. So you need to then type grow fs because this was a UFS file system. You may also want to label it via Geom. You type glabel, you're going to label some label at your partition. You then check if the partition was created, and you can use it now you can create a file system using the label instead of the raw partition name. You mount it, you create a directory and you mount it. You may also may want to encrypt a partition via jelly. You create a partition. Let's say we create a partition. We type jelly in it, our new partition that is labeled as secret. We attach it because it is encrypted. It will ask you for your password. And then you create the file system and mount it. So as you saw on the recent examples, to create, to row, to label, to encrypt a partition in FreeBSD, it is very powerful, the storage stack from FreeBSD. It is built from clear composable primitives, the GM framework. However, that same composability pushes complexity onto the user. For partitioning, encrypting, labeling, file system operations, you need to know a lot of tools. I don't know, but I always get confused to what to type. I don't know if you too. So that's why I present GeoMan. So what is GeoMan? GeoMan is a text-based disk management tool for FreeBSD built on top of BSD Dialog. It provides a simple terminal user interface to work with partitions and file systems using the GeoM framework. On GeoMan, you can create, copy, paste, label, encrypt partitions. And it supports you can also grow or shrink a file system depending on the file system, because there, for example, UFS, you can only grow, but you can't shrink the file system. And GeoMan is not a completely new tool by itself. It is underneath is SADE, SADE, and adds some functionality. You have probably, if you have installed FreeBSD, when you are installing it, it is the same as typing BSD install per edit. So the same tool is also known as BSD config disk management or SADE. It's the same. So I took that tool and expanded it forward. Here's an example. Now you may have seen this similar UI. You can see it's different from SADE because I have added a few functionality, but here's the interface. So this you can copy, you can paste, and there are obviously the typical things that SADE had. For example, you can create, delete, you can modify, but you can also now check, for example, file system. But is SADE the best way? I mean, isn't there will this be the better approach to create a new partition management tool in FreeBSD? You may think of porting gparted or KDE partition manager. You may want to build a new tool from scratch or extend SADE. The goal was not only to provide a partition editing tool, but to build a native storage workflow around GeoM, file systems, and CFS, something that allowed you to declarative create anything related to file systems and storage in FreeBSD. Why not port gparted? It is mature, yes, it is well known, but it's not designed around the FreeBSD storage model. If we wanted to port gparted, it will have some drawbacks. It will depend completely on gparted internal design. It may become difficult to add specific FreeBSD features on the UI. And because the approach that FreeBSD has is very different from Linux, I mean, Linux doesn't have GeoM, it will be missing some concepts as jelly, glabel, what is a provider, what is a consumer. So it wouldn't fit naturally. and at the end we could diverge too much from the upstream. So isn't worth it. But why to extend SADE? Why to use a tool that FreeBSD already has? It avoids a large graphical user interface. Let's be real. You use FreeBSD a lot of times on servers, and you don't have a GUI. So it would work on servers, remote machines. You could SSH, because it is a terminal user interface. You won't be worried about it. It is a smaller code base, so it makes it easier to add new features. And it is thought for FreeBSD. I mean, SADE has existed in FreeBSD since 6.0. So a very old tool. So by extending SADE, we give users an iterative storage tool without requiring a desktop environment or importing another storage model. We will be using what FreeBSD already has done, and it will work immediately. So let's first try out how you can use Geoman and what new feature has been added compared to SADE, which is a classical partition management tool from FreeBSD. You can now create more file systems. For example, if you install the NTFS port, file systems NTFS port, you can directly create a new partition. For example, you just type the type, the type of the file system, the size, if you want where are you going to mount it, and for example here, 300 megabytes. You can also create the ext file system from Linux. You just need to install this port, and you'll be able to create the ext partitions on Geoman. And in this case, for example, it is 900 megabytes. What else we have? You can grow, as I said, partitions. If you look at the left, you have the devices. Here you got the partitions. So let's say we want to grow UFS file systems. It was 500 megabytes, and now you want to grow it to 2 gigabytes. Well, you can see where you can select the modify option, and this menu will appear to edit the partition. So you can type in a new size and select OK. You can also shrink a file system. Linux file system ext can be shrinked. So if you here is clearly, you choose modify, this menu will appear, and if you look here, this partition ext4 was 600 megabytes, and now you can resize it to 500. So you can do that on Geoman. And a new interesting feature that you might be interested in is to copy and paste. So for example, here you have a ext file system, 500 megabytes. Step 1, you will have to choose on copy, select and choose copy on the partition, and then choose the device where to paste it. So here we have it is on the same disk, yes, and you paste it. And then you have to select an offset. Maybe you don't want to paste it right after all the other partitions, you can move it. Red means the taking space on DA2 on the device, and the blue means the partition that you are pasting. So here appears exactly the offset, the starting point and the ending point. How much size is it? You can modify only the start and the end, right? But you cannot. You can also perform other tasks, not only creating, growing, or this type of things. If you remember, we were labeling and encrypting. So pretty much the same. Let's say you create a new partition, and here's the menu, and you can add labels. You can add glabel, which are the geom labels from the framework, or you can use a partition scheme. In this case, GPT, you can add a GPT label. You can add any of both. You can encrypt a new partition when creating it. So before choosing OK, you will choose encrypt. Here's the size, some type. And the same algorithms, the same process as Jelly, right? You choose an algorithm, you may pass a key file, a pass file, or you might type your password. Passphrase or pass file plus a key file. So you can encrypt right in Geoman. So we compare manual commands versus Geoman. If you want to create, you have to type gpart add, then create the file system with tools like NeoFS for UFS, this one for ext, make file system ext4 in this case, or make ntfs. With Geoman, you just simply select free space, you choose some size, which file system, and confirm. To grow, the same thing. You need to first type gpart resize, and then grow with, for example, grow UFS. With Geoman, you just select the partition, enter a new size, and confirm. To label and to encrypt, the same thing. Glabel, here you open a dialog and apply. Or to encrypt, you need to be careful with jelly init, then jelly attach. But with Geoman, you just click or choose the encrypt dialog, choose an algorithm, and apply. Nothing else to do. Manual workflows are imperative. The user must know the exact commands, tools, orders, flags, and devices names. But Geoman is declarative. The user selects what to do, reviews the plan, because you can look at the commands to be executed, and simply apply it. For the future, what am I thinking? What are some nice features to add to Geoman? I would like to add support for more Geom classes. Geoman has a few. Practical CFS management. I must say that CFS is a very important feature from FreeBSD. So Geoman must have at some point support for CFS, so you can manage your pools. You can maybe create mirrors or RAID. A safer partition way to move a partition. I couldn't find a way to move without creating a backup, so this would be nice. At first, I tried to use simple partition management using DD, but it can corrupt the file system after relocation, because DD copies raw the partition, but for example, the offset or the metadata on the blocks changes because you relocate it, so you can't use DD reliably. And eventually, the final goal is to add Geoman to FreeBSD, because currently it is support. You can try it, but I will try to add it to the base system. But before that, I need to add the features I mentioned. Testing, and obviously, that's why I am here, to get some feedback. I would like the FreeBSD community to try it, so to get feedback and improve Geoman. And most importantly, time. I need a lot of it. Here are some links if you are interested in Geoman. This is the source code. You can find here on GitLab my repository. If you want to install it, here's the port under sysutils geoman. So you can install it and try it. And we also have a channel, Libre chat, called FreeBSD-geoman. So if you want to talk with me, I mean, I am there, only me, alone. You can talk there. And here are a few things nobody asked for. I was a good summer code student, 2024 at CERN, and 2025 at FreeBSD. That's why I am the author of Geoman. I developed it under Google Summer Code. I am a computer science engineer. I am a president of a club back in my country. And finally, I would like to thank my mentors. Robert, he couldn't come, but Alfonso, sitting there on the blue shirt, I would like to thank them because they were my mentors on the Google Summer Code project. So finally, if you had any questions, I would like to hear them. Okay?
Oh, wait, one second. Okay.
On the slide where you had said that manual workflows were imperative, Geoman was declarative, you mentioned that you could review the recipe, but you didn't really get into it. Review the generated plan.
Yes,
so is that
list
a
of
feature
commands
to be installed, or can you view the recipe before you execute it?
Yes, you can be. You only look at the commands to be executed. You can't modify it. You can only see it. Yes. Let me do a quick test. For here is. So, for example, let's say you want to modify the size or create. I don't remember which one recorded the let me see. Here, for example, after you do any action, either creating a file system, a new partition, labeling, encrypting, at the end, right at the end, you see the command to be executed. So yeah, it is shown. Another question?
Thank you. Do you have the the ability to edit the plan of ZFS data sets that are going to be created? I suppose ZFS is going to call them the
CFS.
Data set. Yeah.
No. It currently doesn't have support for CFS. But I have to add, for example, to create pools. Yeah, but currently not.
Right, and with BECTL and whatnot, you need to be creating like the dummy user and var partitions that aren't really mounted and so on and so forth.
Could you repeat?
Something your mentor might get to you. So if you look at ZFS, the boot environment control basically makes root extend into user and var, and those. There is a user and var created in the ZFS tree, but they're not mounted. They're there sort of in between the file systems. And this is created so that the boot environment, we're getting into another kettle of fish here, but there's a number of different types of things that are created on ZFS, and I was wondering if you're looking at them, but obviously not yet. So.
ZFS, time is not very difficult to add some feature in the way it is to do.
we can add in the future some ZFS support.
Right. The only reason I'm asking about this is because you often create this the reason I'm asking is you often create this at install time. And so customizing what it's about to do, it's a lot of work to refactor that afterwards if you wanted to change it. And so I assume that this is going to be inserted into the install process.
Yeah. The idea is this is for no installation, probably in the future for installation. But okay. The idea is for installer, but we should work still on it.
I'm wondering if you have any thoughts about your experience with Google Summer of Code. Was it a positive experience? Were there any things that could be better? Yeah, just any comments you have on GSOC.
Yes, I must say that Google Summer of Code is the best experience. I mean, first time it was a bit easier because it was another language, a programming language, but this time on FreeBSD, even though it was way harder for me, first time a real project using C, and not only that, but also I had to learn a lot about FreeBSD and the geom internals. Yeah, even taking into account that, all that complexity, it was still a very good experience. I must say that. Everything was clear, mentors right on time always, good reviews. Yes, it was nice. I can't find something bad about it. So thanks for coming, and that was the talk.
very small. So, yeah, good travel, perfect for travel, and very customizable. All the orders are
Sure, whichever. I can move if you want. It's up to you. All right.
So like it's perfect for home. Yeah. So it's better here. People weren't used to it, say, oh, it was so bad. But once you get used to it, it's like really.
Cool. So it's 3:45. Give it like, I don't know, another 30 seconds, a minute to let somebody come in and then get going. Cool. All right, so I'm going to start. Hopefully you're in the right session. There's a lot more than I thought, given who else is talking at the same time. So thanks for coming to hear me talk. And more to the point, hope this is actually somewhat interesting. Let me start out by simply saying that you should not do this. There is a use case for this, but the use case is very, very, very small. It is unlikely that you have this use case. This is something that I wanted to see if I could do and how hard would it be, and use that as an excuse to kind of come say hi to everybody here. But just to be very clear, you should not do this. So what I'm going to go over is how I built this thing, which is effectively a stock SSH client that I SSH to an IP. It goes to one of a few different nodes, right? And then that machine goes down. The connection that I'm talking to is literally like the machine hard goes down. And my SSH session stays alive, and I can still keep using it. So for certain applications, this might actually be useful. 99 times out of the 10, or 99 out of 100, you don't want to do this. But I designed this mainly as a way to say, if I was in an emergency situation and I wanted to use this kind of mechanism as what amounts to a war room, instead of like an IRC server cluster, which is the traditional hackery kind of, we'll make it work no matter what, kind of the world's on fire, it'll still work. You could use something like this, and because it's SSH, you can tell all the people that need to SSH using this key, it will get you in, and then from there, your connection will always stay live, even if one of the 3 or N of M servers go down or providers go down. This is starting to slide down. Oh, there we go. Sorry, dude. I put it on that. I'll keep an eye on it. But yeah, so that's what we're working on and what this presentation is about. It does work. You should not do it, as I've said before. So I ended up having to terminate TCP in user space. This is because the OpenBSD kernel is really good at what it does, and it also doesn't allow you to just randomly, from a high-level architecture perspective, if you have 2 machines and you have a packet coming in the door here, and you have the kernel in OpenBSD actually doing the proper TCP stuff with it, there's no way to just say, hey, kernel over here, this other one. start this at this point in time. It doesn't do it. Linux, sorry? Set diff. Okay. Yes, I will. Okay. It's also, there's reasons why you might not want to do that. So the send diff comment is appreciated. I will consider it, but I don't think it would align very well. So in Linux, they have a thing called TCP_repair, which is basically allows you to, with the appropriate permissions and caps in Linux, to say, hey, kernel, you need to start a TCP session with these particular attributes. And that involves like the counters, along with all the state, along with the for tuple for the source destination IPs, all that stuff. OpenBSD doesn't have it. Arguably, it shouldn't exist in the first place. This is me basically saying, I did this by using user space. It's worth also mentioning, we'll get into it. I originally thought I might be able to do this and then realized that PF is not the same as the kernel because I traditionally use OpenBSD for a lot of stuff, but mainly as routing and mainly as firewalling at my edge. And the result of this is that I went, oh yeah, I'll just run PF sync, it'll be fine. And that's totally fine if I was routing across to another node, but not terminating on OpenBSD itself. Basically, again, just to make sure everybody's on the same page, you should be using tmux or mosh or screen or take your pick of whatever, just a normal SSH session, and then running something that allows you to get back into it. This is a very weird edge case that you shouldn't use. This kind of goes over why again, but seriously, use tmux or screen or whatever instead of this. Also, in case it wasn't obvious already, I do this for a living, not this, but like I do software development stuff for a living, and there's been a big push where I am to do AI stuff. I'm sorry. I did this. I'm not committing this whole project to base. This is all agentic stuff. It does work. I'll go through it if you want, but it's a separate conversation. This is not going to be about AI. This is simply a statement that if you have seriously strong opinions about this, be aware this is the case. Yeah, I wanted a reason to do it, basically.
I retract the sentence.
Yes, exactly. So just to be clear, yeah, if I was doing the diff stuff, I would not be using this. So. Yeah, I also used spec-driven development, which is basically just aggressively saying this is how this should work, get the stuff to do it, blah, blah, blah. But that's a separate thing. So just as a standard disclosure. And I'm not going to be offended if that offends you, because people are different. That's allowed. Basically, this is what we're going to go over, as I mentioned, really roughly speaking. Yeah. As we were talking about, different levels will do different things. So we've got routing, the TCP connection stuff, and then the SSH crypto stuff. Think of it like a standard stack. Routing, you can use any casting or that kind of stuff, VIPs or like virtual IPs, and just do routes, whatever you want, depending on where you are in the world. Like if you're in a VPC and you want to do this, you can just set the static IP on the different machine or route it or whatever. If you're on the global routing table, BGP, and then you have to care about which node you're hitting a lot more, because then you have to start to influence that, right? So if I'm running 3 in geographic, you either have to handle a case where packets are coming into what amounts to not the leader, right? And you have to replicate those, or you have to say, no, go away and go over here. But because it's a stock client, you actually want to backhaul the traffic. So we'll get into it, but there is a denial of service vector here, straight up. Because if you throw packets at the door, it's going to forward them over without touching them really to whatever the leader is, and that leader might not be the same host. No broken pipe, no reauth, no renegotiation. I should be able to yank the power on this thing and have it work. And it does, which is nice. That's, again, just going over not all of it, but some of it. I can't stress enough that you probably don't want to do this. I've said that I think 4 or 5 times now, but like the closest thing is probably like a weird implementation of Quick with like SSH, because it has the idea of basically sessions, and so you can change the for tuple underneath it, but that wouldn't be the stock client, right? Like that wouldn't be stock OpenSSH on your client side. So as far as I'm aware, there hasn't been a stock OpenSSH client that has this kind of stuff before. What most people do is they use what amounts to either VMD, although that feature got taken out about a year ago because nobody was using it, the live migrate off VMD. But in Linux, that's pretty standard. And usually people are like, we'll just do that. And that's how all the major cloud providers work. And so you have multiple machines, VM is up here, I can live migrate the VM, it copies the memory, and the TCP session goes with it because you're copying usually the entire guest memory, including all the processes and everything else. There's a bunch of stuff in here, and again, full disclosure, like this graph over here is probably not correct, but it's close enough for the purposes of like heads up. There are some things that do this, but they don't do the entire stack. They don't go up to the SSH session. So there are schemes that allow you to what amount to create a buffer of TCP, so you can send traffic from one client to a server, let's say, and if it doesn't get there, it'll retry it, it'll replay it. Those kind of protocols do exist, but you can even get it to the point where the SSH connection will be sort of working, but the SSH protocol will break because you're going to have packets that got there and the thing's going to be like, what the hell, no, you already talked to me with that like nonce or something similar to that. Yeah, so we ended up using user space for this. And this is the one big thing here, is this allows us to never have a case where a failure will interrupt the client. So the client will not get a TCP reset, is the idea. And all of the crypto SSH state will actually stay the same and consistent across. So let's go over the routing. Basic stuff, 3 nodes, does the thing, right? Basically, your traffic goes to one of 3, and you don't get to decide which one all the time. Your ISPs in the middle and the internet topology get to decide this. It's worth mentioning that this is actually totally valid as a scheme, this whole talk, without any cast at all. There are reasons why you might want to do that much more. So if you have 3 physical devices that are stacked to each other and you want to make damn sure that they're all up, you can run a quorum on this, and it gives you SSH that is HA'd in a similar way to like etcd would, or yeah, basically, there's nuances there. I would recommend doing this with 3 nodes that are in the same VPC or in the same geographical region at least, because as we'll see, the latency gets up there. The way in which this works is packet comes in the door, it then has to be in a committed state across the majority of the nodes, which means that you're incurring latency to transit that from whatever node it came in at to the majority of the other ones. Doing this across the globe, across the Atlantic, is roughly 200 milliseconds. Doing it to Asia would be 4, roughly 3.5, 4, 100 milliseconds. So if you're clackety-clacking, it's going to be noticeable. BGP does have convergence windows. And what that means is it is possible for your internet service provider or the general internet, it is not likely but possible, to have a route that actually changes that results in there being no route to that host for a little bit of time. If you're advertising from multiple places, theoretically, your system, like the internet routing table, will actually immediately switch over to the next one, immediately being relative, but like it'll switch over and it has the notion of there are 3, there are X, I'm going to pick the best one. But there are cases, specifically with smaller ISPs, where you can have 2 upstreams and they have to relearn all of the routes, and that can take some time depending on the hardware. So it's possible that this doesn't actually cover your case. Did I mention you shouldn't do this? So you can nudge. The biggest thing with any casting is this is going to offend a whole bunch of people in the room who are network related, but like just prepend your shit. By that I mean the way in which that works is you say, hey, I'm here. You announce some routes or some other details with that. you can choose to make that longer. You can choose to basically bias it saying, please don't come here, please don't come here, please don't come here, but it'll still be valid if you do. And so that's one way in which you can kind of suggest strongly that the world comes this direction to talk to you instead of coming from another direction. There is also the idea of a med, but this goes into BGP stuff that isn't really part of the talk tons. Basically, I'm just trying to make a point that you can influence where the decision comes in, but you can't control it. Also, my basement had some water in it last week. So I got to the point of it works, and I have a demo for you. I have not pushed this out to 3 nodes across the Atlantic. I have it in a VPC that works. But theoretically, it's all done at layer 3. There should be no actual issues with it. And it's been tested and all this other stuff, but heads up. That's more stuff about, this is the big thing. So there's no TCP state. Because of the way in which this is done, we actually had to take basically PF divert. So when a packet comes in the door on the egress or on the ingress interface, it jumps into a program. The kernel doesn't have any consideration of what state that's in at that point. It then gets re-injected back, but basically there's just a line that is diverted straight up into, and as a result, if a packet comes in the door, it hits a divert on one node, goes up into the application, that might be transited all the way over to a different host, right? So you do have a problem of SYN flooding will mess up your entire network, and there's a bunch of other security concerns because there's no way for that follower node to, I guess there is, but the way in which it's implemented now, any 4 tuple will just get forwarded on. So you could spoof TCP packets and it would go through the network. It would fail at the other end, but it would still go through the network, incurring cost. So, kernel stuff. Kind of mentioned it off the top, but basically the TCP, PCB, so the actual connection that exists in the kernel, it's not meant to move to another kernel. And there's no way to inject that. And as a result, for this to work, it needs to be done in user space, because even if you have all of the other layers where you have the SSH and you have the TCP stuff, it's the TCP at the kernel level is going to simply be like, no, go away. Because it doesn't have this would not be the case if you were forwarding though, which is just basically what pfsync is, right? So pfsync and carp on the front of it, or pfsync in general, you could then just forward it along. But you have that problem where you have to terminate at some point. So that's why we ended up going with like that. Yay, there's the same visualization just for people who may not, whatever. This, very clear, this is the problem, and this is what this solves. I think that's terminates everywhere. Yeah, that's basically, it's the terminating thing. So just to be very, very, very clear, it's the termination of, not the routing of. That's the problem. We talked about TCP repair previously. Also, there's protocols like MTTCP that exist in some other distros, and you might be able to run them over the public internet. You probably can't, a lot of them. I mean, you could backhaul SSH off of SCTP or something too if you wanted to, but it's unlikely that you're going to. So running a stock SSH client, you need just stock TCP and just have it done. So we talked about this, reroute live in flight, blah, blah, blah. Termination, we talked about that. Any questions about this? I'm kind of flying through, but it really is like, hey, this works, it does the thing. Yeah. I feel like I'm talking to a crowd of people who know what the hell I'm talking about, so I'm kind of skipping a couple slides that reiterate the points that are relatively important. So, yeah, that's the big thing. So it's a divert on the PF line that goes into the application, and then the ACKs are shoved back. It's worth mentioning that when I stop and think about this, if I was ever going to do this, I actually would want to run this as a user space TCP implementation anyways, because of the security model that it represents. It would allow you to use pledge. I mean, this does use pledge, but it's pledge that's wide open for network. So the bigger thing is you could start to limit it down a little bit more with other tools as well. And so putting it in user space might actually be a better call. And from a kernel level security posture perspective, having the ability to suddenly mess or inject TCP connections might not be the thing that OpenBSD wants to do. Maybe, maybe not. It's definitely something that permission is pretty aggressive and allows you to do some nasty stuff. So, following the packet goes bit anycast, pass in straight up to a particular port. It's a divert packet, right? So packet comes in the door, goes to an application. Technically it goes to a port that then has an application listening on it. And this is a PDF because I didn't want to hit the, sorry, I'm scrolling. It then holds it, as I mentioned earlier. At this point, it has the 4-tuple, right? And it's going to commit that into the state. It's not going to reply back. So you actually have a client that has a TCP like SYN out the door. It's not going to SYN-ACK back until it actually goes down. So it has to send it to, in this case, Raft. I think the slide got cut for brevity, which looking at the time probably was a mistake, but we don't need to go over it tons. Raft is a very simplistic, relatively speaking, it's nuanced quorum system that allows you to have simple majority quorum and has the idea of a strong leader, which means at one point in time, one machine is making the decision. And as a result, when a packet comes in the door, the actual encrypted packet gets shoved into this system and gets stored. And it's not doing decryption at that point. We'll get to the point where some of the crypto's in here, right? It's the entire packet that's already been encrypted. Because there's a case where as soon as you accept the packet, that machine dies. You want to have a record of that packet. And yeah. There's an architecture later, but effectively these nodes, so this entire system is in Go. And each node basically exposes, it takes a divert hook in for packets, does the SSH stuff, does the Raft stuff, and also to do the Raft quorum, it talks using standard like MTLS or mutual TLS to other nodes, does the thing. So any questions about this? I think I kind of breezed past a lot of stuff. I'm getting, no, good, okay. I just want a sanity check. So it re-injects it, that'll go down kernel, it'll go all the way out. And so you'll see it in the PF state at that point, because it'll be there. So it's worth mentioning that if you're running a stateful firewall, you will need PF sync as well, because some of those connections, technically I don't think you need it, but you might. By that I mean I ran it without and it was fine, but I was also playing around with PF enough that I think I had it, yeah, doesn't matter. You might have reasons to run PF sync across the nodes as well. And it's also worth mentioning that as a proof of concept, I did this exact same thing, but I basically did it with PF sync traffic so that I could run it synchronously. By that, I mean PF has the notion, or PF sync has the idea of either best effort, which is pretty damn close to all the time, or synchronous. And it won't actually say yes until it's got an ACK back saying it's replicated on the other system. Well, I just spoke PF sync on this side and had Raft on the back end, so I got the same kind of consistency guarantees. That is an option as well. So, kind of went over this already. It crashes before the commit. It's a TCP retransmit because it didn't get an ACK. If it gets there, it actually ACKs it, right? So there's no way in which the client actually doesn't keep the connection open. It's a raw socket because we can't use the TCP that exists in the kernel, as I've been saying for the last whole thing. It does have pledge. It's kind of useless because, well, it's not useless. It's very limited because it is basically raw IP TCP, or IP. And so as a result, the binary is limited down to like standard other pledge stuff like writing or like to a file system or certain things like that. But it is, you do give it straight up all network access to facilitate this. The Raft, inside the Raft system, basically the Raft log, so Raft works by an append only kind of thing. And then, so append only being a leader can add to a log. That log is then replicated everywhere, and followers follow the log. And then once the majority of systems have actually said, yes, I have this log, it gets removed off the back end. So it's kind of an always forward rolling log, and then you can remove stuff off the back end. This is kind of an example of, well, this is legitimately pulled from the code as to what one of those entries looks like. So packet comes in the door, you have some SSH state, all this other stuff, but you also have the 4-tuple in there because you need to be able to match it. And in case it wasn't obvious, the Raft log contains a lot of information that should not leave a host under normal circumstance. So it has not just the private keys for the SSH system, which is, I mean, pretty much all you need. It also has literally the keys per session, right? So the way in which I had to do this was I used off-the-shelf Go stuff, a Go server, Go SSH implementation, and then hooked in and basically exposed those private keys from that library up, and so from there you can do what you want with them. But this is the crypto that's actually running your particular session. It's worth mentioning that this is a straight up fork. By that I mean I lifted the code and it runs. You shouldn't do this, as I mentioned, for like the 6th or 7th time. The system does have kind of cluster-wide key stores as a result. So I will get into it, but you can basically say, hey, I want to add, this SSH key should be allowed to come in. Okay, fine. That gets replicated along, because you're already replicating other stuff. So we're using the same database or the same Raft storage system for a bunch of stuff. Some really fast churning, every single packet gets committed stuff, and some longer term lived stuff. And it's also worth mentioning in here that like outbound ciphertext and offsets in there. So because of the way in which a lot of this crypto works, it has a whole bunch of counters, it has a whole bunch of nonces in it. Whoever is the leader in Raft parlance, there's only one server at any one time actually doing the connection. It's just simply that there's enough state shared around that any one of the other ones can pick it up immediately. So as a result, only one thing is doing the encryption, and then what amounts to it queues the packet egress, because it's possible that it dies by the time it's done the encryption for egress and it didn't make it out the door, and the client is like, what the hell, basically. So it's kind of for really simplistic purposes, which is pretty accurate actually, you can think of it like a buffered back and forth. So ingress and egress are buffered, and there's shared quorum, and there's some state, and as a result, as it goes out the door, it's also buffered. So Raft has a bunch of stuff. You can, some of the things that you can do, basically Raft uses a finite state machine, and it's a replicated finite state machine on top of a replicated log. And as a result, this finite state machine, you can define your own operations. These are some of the operations where it's like, okay, I want to actually say, I have a packet coming in that matches that I need you to queue in case I die. Or I want to update certain things, like before we actually egress it. It's really important stuff that if you don't think about will cause problems, like pruning. Every single bit of data that goes over, every single packet that hits this system ends up going through at least the majority of your cluster. And as a result, it's high bandwidth, relatively speaking. It's a multiplier, it's a denial of service vector, but it also is, you need to churn off the bottom of that. Like you can't have a slow client. If you're gonna implement this at all, which please don't, I would highly recommend 3 nodes that are in the same geographical region and have them spec'd similarly. Because if you have a slow follower, it will cause problems. I think we've mentioned this, but same thing going the other way. So only one leader decrypts. So packet comes in the door. There's a log of raw encrypted packets from the client coming in. Those get committed into the state. The server then pulls them off, decrypts them, and shoves them into the committed state as well, right? Well, acts on them. So in the transition period, you've got that committed state. So if a packet comes in and the node dies immediately, the next leader is going to do a sweep. Basically, when it comes back, when it's like, oh, I'm now the leader, it looks and says what packets exist that came in that haven't been handled. We talked about this stuff. That stuff's solved. So we talked about routing and TCP. That's great, because the 4 tuples are there, right? So everybody's good with the 4 tuples. And we're using divert and a user space TCP system. So presumably, the system can go, oh, OK, I had a connection open. So we've built up to NC already, or what amounts to that. It's worth mentioning that cipher state is aggressively churned in the terms of nonces and that kind of stuff. And this is done generically. So yeah, that's all that stuff. I ended up limiting this to some crypto systems that were, or some crypto algorithms that were supported by OpenSSH, because the library this could be applied to any of them, but the reason why I did is that the Go SSH server implementation that I was using exposed a decent number of them for certain algorithms up already, but it didn't expose all of them up. And so I just disabled them because I wanted this to work, and if you care about this, you can go and make it better. We're also not storing plain text because basically it's byte for byte, it gets encrypted once, shoved out the door. We talked about this, buffer. I swear this is getting close to done, and there's a demo, so I'm just trying to get, there's the restoration sweep we talked about, right? So in case this wasn't very obvious for the people who are visual, as soon as it comes online, goes through the packets, does the thing. Drive link connection in user space. So yeah, what it says on the screen basically, where we've gone over this a few times now in a few different ways. There is actually a little bit of state that in the Raft system itself, you have to have log entries that are pretty aggressive because of that. At the exact instant of that switchover, you will have slop. You'll have difference from when the process died and the committed stuff died and when the packets are coming in. And so you have to handle basically what amounts to the entire buffer on both sides. The window that you're dealing with has to be larger. The window of your slop has to be bigger than whatever your edge case is for network traffic versus for ingress traffic going in versus going out. Yeah, and we mentioned this earlier. Latency. Attack surface, there's a forked SSH server. And this can be done, but for the ease of basically SSH rekeys, and I didn't add in yet another log entry type for the RAF system, so that as it rekeys, it'll just fail. This can be solved trivially. It's just those rekeys happen so quickly that there's not much point to add them in, because they happen once every X period of minutes, depending on the algorithm. You can add it in. It's simple enough. And just to make sure everybody's aware, it's relatively straightforward, right? So it's just MTLS across 3 nodes, SSH server on each one, and each one has a relatively straightforward, similar system. The system is set up with a proper CA and then MTLS verification on the back end of it. And it uses, for command and control on the node itself. When I say command and control, I mean what's the status of this? Or add this SSH key, please, so that somebody can log into this. It's a Unix socket. And it is on disk as basically it's not LMDB, but it's close. It's a Go implementation of something similar to LMDB for the storage. So it is hitting disk, just to be clear. but you could RAMFS mount this or whatever else you want. Running it looks like this. Basically, it's a binary, you run it. It has some options. The options are what you would expect, where it's just telling each other where the nodes are, the TLS certs, whether or not you want it to bootstrap or whether you want it to come up automatically. By that, I mean, if you start 3 nodes, they need to form a quorum, and you can have them just be like, I should join an existing quorum. So there's some flags for that. And then, as I mentioned, you end up talking to it with basically nc-u over a socket. So you can just make this work, script it however you like. So I'm going to try this. You guys see that, hopefully? Oh, yeah, okay. Okay, so this is 3 nodes. The status on the top right is refreshing, and basically giving you the status from each node. There's a while. I'm going to pause this one up here. So this is basically a SSH-T to the actual virtual IP address, right? So basically this is SSHing in, like you normally would, and then it's running leader uname-n. And the reason why it's prefixed is I want it to execute an actual command. Well, you're logged into a machine you're logged into an SSH server that could magically swap at any point to any different node. So I just prefix it with leader, then you can run a command. Obviously, this would be where you'd put your own application stack, right? So if you're designing this and going to use it, you would have it drop into what amounts to a TUI of some kind that was always available and talked using the RAF system or something similar, so it was always available. Anyway, so this thing is basically going down and just like, if I go over to this terminal and hit enter, it kills it. In this case, because I didn't, is there, it not only killed the leader, it also went and moved a virtual IP address on one of the nodes, but that is trivial and can be done using BGP or other routing systems as well. But as a result, you see up here, there's one of them down, one of them's a leader, one of them's a follower. And over here, this changed. It's subtle, but you can see it if I scroll up, where the existing SSH session went from node B to, or node, from node B to node C. Node B to node C, right there. So that's where that happened right there. And this SSH connection is still live, right? And I say, okay, I actually want the status. Great, it's still there. Notice that there's weird edge cases like this where the uptime's different and the session's different. It's still there, but this is the replicated state not being perfect across the entire cluster because I made this work. But if I type in leader, it's there, and great. You can do stuff like this, where node up, which one was this? So now it's up again on that, and you can do stuff like down, which is the current leader now, node C. Great. And you saw it switched back over to B. And now this, if I type it again, it's on B. So basically the SSH system was kept up across both. There's the demo. Any questions about the demo? It's relatively straightforward. It's also just like, hey, look, it worked. Yes, congratulations. The talk, what you said on the thing was what it did. Does anybody have any questions about this? I've got 1 or 2 more slides, but they're basically wrapping up. Yeah.
Hold on.
Oh, okay, sorry. There's. I can do the go around. Thanks, Charlie.
Yeah, my question is, what's the benefit of doing this versus if you have a script to say just SSH and try different nodes?
So the benefit would be very specifically long-running SSH connections where the simple answer is, if you design your system properly, there isn't. The reason why you might want a long-running SSH connection open is you're running a horrible script that you need to run no matter what, and it needs to, handle fail. It needs to always be there. Or the reason why I built it was, again, just to reiterate, I want a system that is multi-cloud or multiple networks, and I want to make sure that if I SSH into it, it's going to work. And I usually put in an expletive there, like it's going to work, and it's going to continue to work. You could easily do a while true, restart the SSH connection, and that's 99% of the time what you should do. It's, again, why I was mentioning that in the first place. Does that answer the question?
Yeah.
So the simple answer is you shouldn't most of the time. But if you want that connection open and stay open, you can do it. It's just not a good idea. Oh, okay, I'll do the runaround.
First, thanks for the presentation. This is great. It's amusing. I like it.
Thanks.
When you were talking about using Pledge, had you considered maybe hoisting some of those different things that you do just to split the
Yeah. So the
privileges?
question relating to hoisting and more to the point, splitting up some of the processes, yes. Right now, this is a single Go binary that just runs. You could absolutely split it into multiple Go binaries and limit the access down a lot, and it would be a reasonable thing. Yeah.
Yeah, and I know it's kind of like putting a bandage on an axe wound.